So the topic of the presentation is selective transport of phosphate across a modified cation exchange membrane, not an anion exchange membrane as it says in the abstract. So just very briefly, the motivation for phosphorus and phosphate recovery. We want to recover phosphate from various waste streams because basically three reasons. Phosphate resources are finite and limited. Although we're not running out of phosphate anytime soon, this will at some point become an issue. It's also a very important fertilizer that if we could recover it from waste streams, it would give us two benefits: A, an economic benefit as a fertilizer, and B, it would prevent the eutrophication of the receiving water bodies that that suffer from these algae blooms if they're exposed to large concentrations of phosphorus. Current methods for phosphorus treatment and recovery. People are very interested in using struvite precipitation. That's ammonium magnesium phosphate. It's a slow release fertilizer. One of the issues there is that you have to add a chemical. Typically the system is magnesium limited, so you'd have to add additional magnesium in order to get that precipitation. But it is gaining traction and a lot of interest. Traditional ways of removing phosphorus from wastewater include things like polyphosphate accumulating organisms. So this is during the activated sludge process. You can accumulate phosphorus in bacteria. You can then collect that bacteria in the sedimentation step and apply it to fields as biosolids. But again, there's some concerns with using biosolids for agriculture. It's not 100% common to do that everywhere. And a lot of work has been done about using adsorption methods to recover phosphorus. Probably the most common is using various transition metal particles like iron oxides, for example. They form both inner sphere and outer sphere complexes as shown over here on the right. Problem with this works really well. You can actually get pretty high loading of phosphorus onto the various transition metal particles. Problem is actually releasing the phosphorus. If the phosphorus forms inner sphere complexes like here on the left, you actually have to maybe even dissolve the particles in order to release them. It's very difficult to get rid of, to actually reuse that phosphorus. The other big problem is this is not a continuous process. So these absorption processes, you typically have some sort of fixed bed reactor, and eventually you have to replace the sorbent with another material. And we started being interested in this topic. We do a lot of work with membranes, and we're trying to think, well, can we do anything where we have a continuous process, that is a membrane process where we can continuously extract phosphorus from a waste stream. And very brief primer on membranes. Typically, transport across a membrane is governed by either sieving or size exclusion or charge exclusion, such as the case with ion exchange membranes, or a combination of the two, like what you see in reverse osmosis membranes, for example. I'm going to be focusing on ion exchange membranes today. In ion exchange membranes, you have fixed charges in the polymeric material, and these fixed charges will repel co-ions very effectively and facilitate the transport of counter ions through the membrane. So in this case, if the membrane is negatively charged, it's a cation exchange membrane, and it will allow positive ions across the membrane very effectively. One interesting topic that we've been interested in for a while now is these facilitated transport membranes, and I'll talk about that in the next slide. But these facilitated transport membranes have been shown to dramatically increase the selectivity of membranes, if you can get them right. So in facilitated transport membranes, you have a combination of both solution diffusion and some sort of complexation reaction that governs the transport across the membrane material itself. What we do in these facilitated transport membranes, one adds an extractant into the polymer matrix, and that extractant facilitates the selectivity of the membrane material. And that selectivity is enabled by selective binding of whatever target you're interested in with that extractant entity. So in many ways, you have an adsorption reaction on one side of the membrane up here, for example, and your whatever target is specifically adsorbed onto your extractant. It will then somehow move across the membrane and then finally desorb on the other side. And over the years, people have developed three main kinds of these facilitated transport membranes. You have membranes where you have mobile carrier, where the extractants can actually move around. So when your target absorbs onto your extractant, the extractant will actually diffuse across your polymer matrix, and then finally your target will desorb on the other side based on some sort of gradient. It could be either an electrical field, it could be a concentration gradient, it doesn't really matter. These are typically liquid supported membranes, and there've been a lot of work on them, including by some people on this call, and they work fantastically well. They have very high selectivity. One of the issues that people have encountered, though, is the loss of, and these have to be basically liquid to allow the extractants to move, to diffuse through. And you tend to lose that liquid over time. So that's kind of an engineering challenge that has not been solved. To address this challenge, people have moved to these semi-mobile or fixed site carrier membranes, where you have a fixed site that can either be covalently bound or some sort of sterically encased in the polymer matrix. And these sites don't move, and the transport mechanism across these fixed site membranes is by hopping. So your target molecule will absorb onto the extractant molecule, or whatever it is, and it can then hop across the membrane material to the other side, and finally, again, desorb on the permeate on the back end. These extractants can be charged groups, for example, as is the case of ion exchange membranes, but they can also be any kind of other dopant. And over the last, I don't know, 10, 15 years, there's been a ton of work on developing various dopants to use in these mixed matrix membranes, including various nanoparticles, which is what I'll be talking about today. So again, our target here, our goal was to develop a membrane that, when it's encountered with a host of various anions, in this case, it can selectively allow the transport of only phosphate across the membrane. And this is not a simple problem, and to the best of my knowledge, there aren't really good membranes that can do this. And our approach, we were thinking about, well, let's take advantage of some of the intrinsic properties of cation exchange membranes to allow this separation. So again, if we have a standard anion exchange membrane, so this is your membrane material, and it has all these fixed positive charges, typically quaternary ammonium, and you have your various anions in the feed side, and there's some sort of transport gradient or transport force that will allow these or drive these particles or these ions to cross the membrane, and through that hopping mechanism. And these membranes will swell very well, and then the ions can move across the membrane through these fixed positive sites. Problem is that they don't differentiate between the various anions. So they'll allow chloride and phosphate and nitrate and sulfate across. Some people have tweaked the transport rates a little bit, but you still can't get very good separation between the various anions in this kind of situation. In the case of a cation exchange membrane, which is actually what I'm going to be talking about, you have fixed negative charges, again, typically sulfonate, but they can also be carboxylate and various other things. And in these kinds of membranes, your negative ions are going to be rejected. So nominally, you'll have no transport at all of any kind of negative ions, but you have rapid transport of your cations. They can move across the membrane very quickly. It's the same. The backbone can be various polymers. But we wanted to take advantage of the inherent selectivity, or the fact that these kind of cation exchange membranes will not allow the transport of any anions through. And the approach that we took in order to achieve that is to create a mixed matrix membrane that contains manganese oxide nanoparticles as a dopant. So that's depicted here, these brown particles that are embedded throughout the membrane. I'll show you some actual pictures and analysis of this material. The idea here is that manganese oxide forms outer sphere complexes with phosphate, and it doesn't really form outer sphere complexes with other anions. And our hypothesis was, if you challenge a membrane like this with various anions, the phosphate, which can form these outer sphere complexes under specific pH conditions or pH ranges, will be able to hop across using the standard hopping mechanism, but the other anions in the system will be repelled by the fixed charges of the other negatively charged fixed charges, in this case, like sulfonate groups. So that was our hypothesis. And sodium or any other counter ion positive cations can rapidly move across to maintain charge neutrality. So let's see what we did. So we took a commercially available cation exchange membrane. We bought it from Fumasep. These are a supported cation exchange membrane. It's very robust. It's actually kind of thick. It has a peak polyether ether ketone support, so you can. It's a little stiff, but it's very robust. And then we formed these manganese oxide HMO nanoparticles in pseudo. So we took the membrane, we did our chemical processing, and we managed to form these manganese nanoparticles that are completely embedded throughout the polymer matrix of the membrane. Here's a transmission electron micrograph of these manganese nanoparticles. They're approximately 100 nanometers, and this is a cross-sectional view of the membrane, and you can see they're kind of embedded all the way through. Compared to a plain cation exchange membrane, you don't see any evidence of these black voids. We did some EDX analysis, and we can see manganese kind of distributed throughout. Again, this is a cross-sectional view of the membrane. It's just kind of distributed throughout the entire membrane. So that was good. We didn't see any manganese in the control in the plain membrane as expected. This is what the actual membrane looks like. So this is a plain cation exchange membrane. It's kind of transparent. When you embed it with the manganese oxide, it turns black. Manganese oxide has a real black color, so it's very robust. You can kind of see it. It's everywhere. And it's a very straightforward method of creating these nanoparticles. We then did extensive characterization of the membrane material. We started off with XPS. We can see that in the manganese modified membrane, we can see the emergence of the manganese peaks at about 642 EVs. This corresponds to an oxidation state of +4 manganese dioxide. We don't see any manganese peak, obviously, in the plain cation exchange membrane. It's this red line here. When we immersed the material in a sodium phosphate solution, we saw the emergence of both a sodium and a phosphorus peak. So that's great. And the other thing that we can see here is that the manganese peak is a little bit depressed. And what happens is, we were struggling with this a little bit, when you immerse these membranes in water, they swell up significantly. Because XPS is such a surface sensitive, it can only probe the first few nanometers of the surface. Even that little swelling of the polymer kind of obstructed the view of the, or the detection of the phosphorus, of the manganese in there. Nevertheless, when we then rinsed the membrane again, we saw the disappearance of the sodium and the phosphorus peaks, meaning that, and that's important because when you make these kinds of membranes, these facilitate transport membranes, it's critical to be able to release the phosphorus at the end because you have to recover it. So we did see that the sodium peak was diminished, but the phosphorus completely disappears. So that was great. That was some sort of confirmation that our sort of idea maybe will work. But it is important to note that these XPS tools are, this is it's a real surface analysis method. So it doesn't really tell us anything about what's going on inside the membrane itself. We did TGA to see sort of any differences between the plain and the manganese modified membrane. And we can see there's the onset of decomposition in the modified membrane starts at about 300 degrees C versus about 230 degrees C for the plain membrane. But again, doesn't tell us a whole lot. All it says is that yes, indeed, there's some change in the polymer matrix, which is what we want. So now for the actual experiments and the actual data. Of course, I was hoping to have much more data and a model and blah, blah, blah. But for whatever reasons, I can blame everybody, including COVID-19. But we have the results, but we don't have the model. So you have to bear with me. We tried two different methods to drive the phosphate across the membrane. One is just a concentration gradient, and the other is by applying an electrical field or a potential gradient. And in this case here, this was our first set of experiments. The feed solution was 100 millimolars of sodium phosphate, and the permeate was 50 millimolar, of sodium sulfate. So the sodium sulfate would be here on the anode side, and the phosphate solution would be here on the cathode side. And you have a driving force from left to right pushing the phosphate across the membrane, either again a concentration gradient or a potential gradient. And what we can see here that under these conditions, we do have some mild transport of our phosphate across the membrane, which was fantastic, which shows that the membrane actually allows the transport of the phosphate across the membrane, which is not what you would expect with a typical cation exchange membrane. Cation exchange membranes will not allow the vast majority of anions from crossing. So that was very encouraging. It's also important to note that the conditions, the electrochemical conditions that we used here are very mild. So there's not a very strong electrical field that is pushing the phosphate across. We didn't really see any or dramatic, electrochemical reactions going on here. So that's also important to note. What are the fluxes that we can achieve using this method? So we tried various conditions, and in the interest of time, I'm just gonna kind of skip over the noise. The main point is under the optimal conditions, and these conditions are a function of the driving force as well. So using the conditions that we tested, we're getting fluxes that are about between 10 and 50 times lower than what you would expect from an anion exchange membrane. So if you took an anion exchange membrane, you would see something like this would probably go to about 1,000 of these units, 10 to the minus 8 millimolars per centimeter square per second. It's kind of weird units that they use for anion exchange membranes. So we're getting transport rates that are, or fluxes that are about, an order of magnitude down to about 50 times lower than what you would expect from an anion exchange membrane. But I'll show you in a second, we have great selectivity. So there's still a lot of work that we need to do in order to increase the flux here. These are, again, very preliminary data. But I was very relieved to see that we were not like, 5 orders of magnitude difference. So I think we do have a pathway to actually increase the flux here and do something kind of interesting. So let's look at the actual separation of various anions in these systems. So this is the control. So this is the plain cation exchange membrane. And you can see here that over time, this is the case where we applied an electrical field to drive the transport of the various anions from the feed solution, which is a combination of sodium chloride, sodium sulfate, sodium nitrate, and sodium phosphate. And we can see here that over time, we don't see a dramatic change in these are the concentrations of those anions in the permeate of the membrane on the anodic side. And you can see that over time, we don't really see much of a change in any of the anion concentrations as expected from a cation exchange membrane. It will prevent the passage of these anions across the membrane. So it's exactly what we want. But when we use our manganese embedded membrane, we can see a monotonic increase in the phosphate concentration across the membrane. And we see, again, we don't really see much of a change in the concentration of the other ions, showing that we do indeed have selectivity towards phosphate, and the selectivity actually quite good. So again, these experiments were run for about 4 hours under very mild driving force conditions. The concentration gradients are small, and the electric fields are not very strong. But we can show that we do have selectivity here, and that was very encouraging to us. So in conclusion, Chris, I'm trying to stay on track, and we're almost there. In conclusion, we've demonstrated that manganese-embedded cation exchange membranes can selectively allow phosphate across the membrane. Other anions do not pass. We haven't found really any significant competition from the various anions in the system. The fluxes are still relatively low. We do need to improve that pretty dramatically, but we do have some ideas of how to do that. And I think maybe to me, one of the most important things is these mixed matrix facilitate transport ion exchange membranes. Maybe an interesting pathway to create very highly selective membranes. We used phosphate because we're interested in wastewater, but really maybe we can apply this kind of method to other potentially more valuable ions that we're interested in, including things like lithium or any other kind of valuable compounds out there. They rely on specific outer sphere interactions to selectively allow the transport of specific species. And I guess the trick would be you have to match your target, your dopant, and the polymer matrix in order to allow for a wide variety of separations. But there's a lot of degrees of freedom there. So for researchers like us, that's kind of interesting, right? We have a lot of knobs that we can twist and try to make something new. Yeah, thank you. I'd like to thank Chris for inviting me. I wish we could be there in person. I haven't been in Israel for more than a year now, and I really miss it. And I'd like to thank the Department of Agriculture, U.S. Department of Agriculture, for funding, and acknowledge Arpita, my PhD student who did all the work. Thank you very much.
Great. Thank you so much, David. That was a great talk. And, you know, unfortunately, you can't hear the applause, but I guess that's the negative part about Zoom meetings.
Well, it depends. It could also be heckling, you know.
So, yeah, you know, there's, I think, 2,000 participants in this meeting, and not everybody can join the Zoom meeting, but people can watch from the outside. But since we've got only 26 people kind of on the inside of this Zoom meeting, I think I'll open it up for questions. And so I'll let the participants actually ask their own question instead of writing it in the chat box. So there's some time for questions. Please, the floor is open.
Well, I have a quick question, David. Very nice talk and nice idea. What's the interface between the polymer matrices and the manganese oxide particle look like? Are they kind of strongly bonded? So
No.
that if you no, okay.
I don't think so. I'm not sure, but I think they're just they're sterically embedded. We grow them inside the polymer, so we don't take a nanoparticle and embed it into the polymer. We actually grow the nanoparticle inside the polymer. So it's I don't think that they're not covalently bound or anything like that in the polymer matrix. So we do know that if the pH swings too low, for example, I didn't show this data, but if the pH is very low, you can actually start getting dissolution of your manganese out of your membrane. So this thing will only operate at above the pH where these manganese oxides will dissolve. But typically that's pretty low. So we have to go like a pH of 2 or something to get that to happen. So as long as you stay above that, the material is pretty stable.
Cool. Thank you.
If I could follow up on Yifu's question, if you're growing the nanoparticle together with the polymer, you said before that you're working with a commercial membrane from Fumatech.
Yeah.
So how are you able to grow a polymer on an existing membrane?
You mean the nanoparticles?
Right, you said that the nanoparticle is grown together with the polymer. But
Well, no, we start
commercial
with
membrane.
We start with a commercial membrane, and then we grow the nanoparticles inside the membrane. We came up with a way we didn't come up with a way. We copied somebody else's way who showed how you can actually do this. And you soak it's actually super easy. It's very straightforward. You take your membrane, you soak it in a manganese salt, like a manganese nitrate, I think we use, and then you immerse it in an oxidizing agent. And because this is a cation exchange membrane, it will load up with the manganese very, very rapidly, manganese ions, and then you oxidize them in pseudo to a manganese oxide nanoparticle. And it just forms these nanoparticles just by itself. It's a very fast process.
Have you tried any other cation exchange membrane to see if it makes a difference?
Not yet. This is actually kind of early days. I was really hoping to have a lot more data to show, but our research is disrupted right now in California. So I'll have to show you what I have. But no, not yet. But actually, that's not true. We tried it with, we originally, what we tried to do was to take we tried to sort of a bottom-up approach or bottom-down approach where we started with nanoparticles and we used Nafion to cast the membrane over them. That actually didn't work very well. because we were encountering problems with like brittleness. The membrane was not just what the dimensional stability wasn't there. We couldn't load enough manganese into the matrix in order to get it to work properly.
Thanks. Nice talk.
Can I also ask a quick question? Yeah, it's a great talk.
Yeah.
It's so great to see the selectivity of this the phosphate ion over the other ions, such as chloride and so forth. Is there any like other potential competitive ions? I mean, you didn't try here, but
Yeah, carbonate.
Bicarbonate. Okay.
Yeah, bicarbonate is probably the other one that we didn't test. I mean, there are a lot of ions out there. I don't know, selenium or something like that. I don't know. I can't. I mean, we haven't tested. We've tested these 3 competitors, the most common ones that people worry about. A lot of, from my scan of the literature, people are mostly concerned of separating these multivalent anions, for example, sulfate from phosphate, because and that's what people focus on. We show that we have great selectivity for those 2, but we also have good selectivity for the monovalent ones like nitrate and chloride. Those are, again, the most abundant ones. Carbonate is an important one, though. We should probably look at that.
Okay, great. Maybe I'll just ask one final question, David. And I got kicked out of in a little bit of your introduction, so what is the? Do you need a weak binding? Do you need a weak or strong guest host binding interaction for good transport?
It has to be just right. If it's too strong, then it won't desorb. It'll just be more like a membrane absorption process where you'll just load up your membrane with phosphate and then it'll never come out. So that's what we encountered when we tried to use things like iron oxide. So you have to find a host that has just the right kind of binding affinity. And I can tell you right now, this is somewhat pH dependent, because as the pH changes, and this is a cation exchange membrane, the surface charge of your manganese changes as well. So I haven't showed this data, but you can actually tune that absorption energy based on the pH, and that will impact the transport rates across. So you have to have a little bit of like a rational design here. You have to find sort of the right combination of the host and the polymer matrix in order to get this to work.
Right. Great. All right. Well, thank you again for getting up so early for us and for your talk. So let's just move on to the next speaker, Professor Yifu Ding, a friend of mine and a professor at the University of Colorado Boulder in USA. And if you could share your screen, he will be talking on engineering polymer membranes with controlled surface patterns for enhanced water treatment. So Yifu, please take it away.
Great, thank you, Chris. Can you guys all see my slides?
Yeah, I can see it.
Okay, great. First of all, thank Chris for the invitation, and I also was pretty excited to visit Israel, but hopefully for a different time. So as Chris mentioned, I'm from CU Boulder, and we have a membrane center, and some of the work was done with the support of Mass Center as well. Oops. Yeah, so this is a picture of where we are. We're at the foot here of the Rocky Mountain, and even though this is probably somewhere in spring and it looks pretty green, but Boulder, Denver area, actually it's kind of like desert, so fits in the theme of the conference reasonably well. So today I'm going to talk about essentially what we have been doing in looking at, can we use membrane patterns to enhance membrane separation. So I think for this audience, we don't need a lot of introduction about membranes, but very quickly is that you can select different type of membranes to look at, to reject, all the way from salt to large particles. And we know that these things are present in different water streams. So for today's talk, we use essentially, we'll discuss essentially ultrafiltration membrane and thin film composite membranes. Basically, I put a configuration of the membrane here. For a typical ultrafiltration membrane, you have essentially a wave of polyester and then porous polysulfone underneath it. And if you only have these two layers, that's ultrafiltration membrane. So we'll talk a lot about patterning of this membrane. And then if you grow a interfacial polymerized polyamide layer, which is typically very, very thin, on top, then you have this nanofiltration or RO membrane. And then we try to pattern them as well. So for membrane-based liquid filtration, and one of the biggest problems is the fouling, right? And fouling kind of generalized in this schematic plot showing basically, now as water goes through, that's what you want to harvesting, all kinds of foulants, right? From all the way biological material to salts. They can participate on the surface or in the pores, which ended up adding these different terms of R. R is the resistance, right? So you reduce essentially the permeation. Now, in membrane community, this has been a significant amount of work, right? Decades of practices try to find ways to enhance back diffusion. The idea is that can you find ways to encourage these foulants or particles move away, right, from the surfaces. And this is a very nice review article about more than 20 years ago by George Belfort, that you can play with all these different methods. But one of the kind of category I want to highlight is that you can manipulate the flow by introducing vortices using different kind of membrane designs, from spacers to curve the membranes, right? But the question we have been asking in the past 7-8 years is that instead of putting a structure like spacers on top of it or bend the membrane, can we actually putting these periodic structure, if you can think of a pattern scheme, right, on top of these membrane itself, right? So that the presence of the membrane, if designed with the right shape geometry under the right flow condition, can promote the back diffusion of these particles. So that's our hypothesis, essentially. Now, I mean, these kind of inspirations are coming from, non-membrane area before, we start working on this, that we know that, there's tons of study have shown, including work of my own, that if you engineer a patterns, these are sub-micron scale patterns, you can orient it, kind of the wetting of the liquid into a very anisotropic form. And Professor George Whiteside's group has demonstrated 20 years ago that if you can put patterns in microfluidics, you can enhance mixing, right, even in a very, very small channel. And you can dictate particle deposition, and you can even control the biological cells, their contact guidance. And by Professor Tony Brennan's group at University of Florida, that they found that if you design structure that mimic shock scheme, you can affect or prevent in a way that biological attachments. So there are a lot of literature has shown that these patterns are at dictating liquid wetting, mixing, particle assembly, attachment, essentially biomaterial. And all of these things you essentially can find in a water stream, right? So of course, we're not the only one or the first one to look at pattern membranes. There's Professor Matthias Westling's group essentially first look at phase inversion micromolding, where you cast in polymer solution on top of templates and induce phase separation in non-solvents to replicate the structure. And here's a review article we had recently to summarize all this work. And Chris, you did a very nice work on printing membranes, by inkjet printing, right? But this focuses, we focus on actually putting structure rather than chemical patterns on the surfaces. So what we actually started looking at patterning is that we want to developing something that we can direct pattern, membranes. So if you take commercial membranes and instead of, kind of do your phase inversion by yourself, there are limitations there for phase inversion. For example, often you get closed pores, and the selecting layer that is away from the kind of the phase inversion front, right? So sometimes it's control is a little bit challenged. So we wanted to see if we can actually just take conversion membranes and directly pattern it, right? That's how we started. And more recently, and I'll show you that the imprinting methods works pretty well for patterning ultrafiltration and thin film composite membrane, nanofiltration and RO. But it has a limitation actually pattern, things like micro porous membrane, like microfiltration, because the pattern sizes we're interested start match the pore sizes. So for that, recently we developed essentially a combined soft lithography with thermally induced phase separation to pattern membranes. So today, majority of the work will be, talk about in this category, and just one slide on pattern essentially microporous membrane. Okay. So the first method we used is direct imprinting, as I mentioned. Essentially, it's a method that developed for semiconductor industry. Right? So the processing of this patterning step basically illustrated in here. You can take a commercial UF, which is polysulfone, polyisosulfone, right? Sits on top of the PES fiber, and you have a rigid template made of things like silicon. And you squeeze on top of it under controlled temperature, pressure, and time, right? Literally, it's a mechanical deformation or thermal embossing process. And then you remove the template, you have your replicated structure on top of it. Now, when we started looking at this, because I'm coming from patterning dense polymer film, right? So we typically do that at temperature that is above the transition temperature for semi-crystalline polymer or glass transition. So polymer actually can flow. When we try that on microporous membrane, on kind of track H membrane showing here, you get a very nice pattern, right? But all the pores are gone, and that's no longer a membrane. Then later, through a lot of trial, and we found that if you do, take this is a larger pore ultrafiltration membrane, right, about 15 nanometer size pores, and you print it at 180 degree, which is about 45 degree below the glass transition temperature of the polymer, right? So polymer is not flowing, but under 4 megapascal pressure, you can actually imprint or replicate, essentially the patterns on the mold by mechanical deformation, right? So first, we investigated what is governing the pattern replication process. So I'll just briefly summarize this, that even though for a dense polymer like polyisosulfone that we started, it has a yield strength. That's where the pressure or minimum pressure is required to plastically deform a polymer. They are typically between about 40 megapascal to about I would say 80 or 90 megapascal here, right, under this deformation. But because of the pores, right, the pores reduce the mechanical strength and reduce the elasticity of the membrane. Now you actually, these are the membranes that we measured under different deformation rates. Now you can actually plastically deform the membrane with pressure about 2 to about 4 megapascal. That's precisely what we used, and we did extensive mechanical analysis of microporous ultrafiltration membranes. And basically, what we found is that the mechanical response, including yield strength, can be reasonably well described by the open cell form, which people have developed for 20 years, used for larger kind of styrofoam essentially, right? But here are pores that are tens of nanometers. And the other important point of that is deformation is really fast. Basically, in other words, that unlike polymer flow, if you squeeze under, if you're patterning a dense polymer film, you have to rely on the flow of polymer to generate the replication, right, patterning. But in membrane cases, because once you pressurize this, the deformation rate is governed by the buckling of the cell walls. So this process is very fast, which is good news for patterning, right? So essentially now, this is what the patterning process is accomplished. You have a silicon mold, rigid, or other rigid mold. you pressurize it, and this is a porous membranes. Essentially, it densifies the membrane underneath, and you have a little bit of shear deformation that squeezes the membrane up. And once you remove it, most of the deformation here is plastic, and they will essentially replicate the structure. And then we modeled essentially how the, the pattern height changes with the pressure you're applying, right? So you can control it by temperature, pressure, time, and we experimentally demonstrate that as well. Okay. Now the imprinting process, because it's pressurization, as you know, that is going to change the pore structure, right? And what we found is that you can kind of connect the porosity with the amount of deformation you impose. Right? You can actually somehow predict the change of porosity. Now, the good news is that because of most of the deformation kind of occurs in the larger pores where it doesn't really affect too much of the permeation. Right? So you can see this is a original virgin membrane before its deformation. This is the top of selective layer, and this is the bigger pores on the bottom. After imprinting, basically less changes on the surface, but on the bottom, the big pores are being squeezed. And we systematically measure the molecular cutoff that measures the kind of pore sizes on the, on the selective side, right? And you can see that under different imprinting temperature and the two different pressure, you get some reduction. So this is the molecular weight. That's a 90% of rejection. The molecular weight, the membrane can reject 90% essentially. You can see it changes from, about 15,000 Dalton to about 10. So you do see a reduction, but it's not significant. And sometimes that's a good news if you want to create tighter membranes. And you can predict how much of this change in porosity and the surface pores translates to the water permeability. And we did extensive analysis on different membranes, microporous, ultrafiltration again. You can actually predict the amount of permeability reduction by the strain, okay, through a permeation kind of deformation analysis. That follows reasonably well, again, with the open cell form. People have realized for those hundreds of micron packaging forms, essentially. Okay, so you can predict it. Now, so that's for the ultrafiltration membrane. Now, what about thin film composite membrane, like, this type of RO membrane where you have a ultra thin polyamide that sits on top of it, right? Now, we tried direct imprinting. Basically, this is a nanofiltration membrane for film tag. And you can, yes, you can mechanically squeeze it. You get some sort of pattern replication, but the uniformity of the pattern, it's not to our satisfaction. Right? But there are groups that have demonstrated that this direct imprinting from, Professor Scott Houston's group, that you can actually use this method, right? But we thought that we want to do essentially something different, okay? So our route of patterning TFC membrane is that since the UF membrane is the support for TFC membrane, and we already learned how to pattern a UF membrane, can we just take a UF membrane like this, right? So this is one of the polyisosulfur membrane that we used for, I've been described so far. And if you just direct grow a interfacial polymerization layer, and that will be essentially our membrane you're looking at using a conventional MPD and TMC chemistry, right? It's a little bit of yellowish color as you often see. But if you take this and directly pattern it, so this is the imprinted ultrafiltration membrane, and you can see the color, and this color is due to the diffraction of light, so the structure color, right, under this condition we have studied. And you can see it's very uniform in terms of pattern transfer. Right? Now you grow an interfacial polymerization layer on top of this patterned ones, and you can see the color changed a little bit. Majority is green now, right? But you do see a lot of area of defects for sure. I mean, that's our base control essentially. But you can grow essentially an IP layer on top of it. And here's the SEM look at the virgin UF membrane. And again, if you grow a polyamide, that's what you look like. You have, depends on the time and concentration you use. You have various roughness. It's very well known in the field, right? Now, if you're imprinting, and this is a patterned UF membrane first, and then you grow the IP layer. And again, here's now the patterned TFC membrane on top of it. And we did a very systematic study of essentially different pattern features, look at line space grading, looking at two-dimensional pillows and pores. And then we grow essentially different pattern height. We take the grading pattern and put patterning using imprinting lithography, look at different heights essentially, right? These are the final performance data, which I'll again show shortly. So the pattern we look at it here is about, periodicity is about 570 nanometers. It's very small, and the width of the line is about 365. And you can control the IP processing condition we did using different monomers and different monomer concentration. Again, these are commonly used by most people are looking at IP process. And then we're looking at essentially even different time. So the quick capture of the process is that obviously if you're using the interfacial polymerization time too long, essentially the nodular structure will take over. Your pattern's completely masked. But if you stay at kind of shorter reaction time, the magic time, no surprising that most people use is shorter than 2 minutes. Sometimes 1 minute works, reasonably well. Okay, so you can retain the patterns, and the height of the pattern obviously depends on IP or the monomer concentration, because that dictates the growth and these structure formation. Now here's a summary of that pattern kind of transfer fidelity. Here's a picture cross-section SEM showing you the barrel layer that is growing on the pattern UF. So we look at how tall the finer pattern TFC membrane divided by the substrate. Now you can imagine if you have a conformal growth, right? So if the polyamide layer is the same thickness both on the trenches and on the ridge of the pattern, you will get essentially the ratio will be 1, right? But we always find that the TFC membrane is shallow, more less shallow than essentially the ultrafiltration patterned ultrafiltration membrane, right? So that indicating you have more growth in the trenches, and that generally the ratios between 40% to all the way to 80–90% when the concentration is very low. Okay, so we can basically control it. And if you grow really like this PIP cases, and you can actually grow almost close to conformal type of growth. But definitely for MPD cases, we get a lot more growth in the trenches, right? So this is, again, this is the original substrate of UF membrane, and this is the polyamide that it grows on top of. All right, and these TFC membranes we did, basically using stirred cells, high pressure, to look at their salt rejection performances. Basically, their permeability is comparable with commercial AO membrane and NF membrane. The salt rejection looks a little bit low; it's about 70–80. But if you, again, this is a study where people looking at commercial membrane under different salt solution pressure, it is very comparable. Okay. So now, essentially, I hope I showed you that we can controllably pattern the UF and TFC membrane. Now let's examine whether such pattern actually can influence the anti-fouling performance of the membrane, because that's the goal, right? So we did extensive studies on different type of fouling. I'm gonna time limit it, and most of these works are already published. So I'm just gonna go a little bit faster here. So we look at a particle filtration essentially using an impinging type of flow. So you have essentially particle or colloidal particles coming down, and we put the membranes that in the cell, and essentially the flow goes radially out. So you can have different regions that are flow parallelly and regions that are flow 90 degrees. So then we took the membrane out after permeation is finished and look at these different sectors, how the fouling occurs. So with our pattern, you can see very nice hexagonal packing of the particle, dense fouling essentially, and sometimes go multiple layer, right? This is the minimal entropy state. Now, when you have the pattern, in this case, what we look at it is 800 nanometer pitch, and we look at 250 nanometer particles, 500 nanometer particles, and all the way to 1 micron particles. In this case, so the line is about, I think, 350 something nanometer, and this is a 500 nanometer particles. And you can see that the particles are guided along the flow direction where flow is parallel to the lines. and less particles found in the 90-degree direction. Right? And then we want to be a little more quantitative look at the hydrodynamic effect, because the idea, what we had, a hypothesis that when you have these structures on the surface and you have a shear flow, the pattern is going to impact essentially the shear stresses at the surface of the membrane, and hopefully it translates to the back diffusion of the particles. So we did a systematic study of measuring the critical flux, where the critical flux is the flux essentially above this value. The particle will irreversibly foul, right? They will deposit on the surface by the drag of the permeation, right? And in particular, on colloidal particle, it's a good system to look at critical flux because there's no absorption, unlike proteins, right? So we measured the critical flux as a function of kind of for unpatterned membranes and a patterned membranes under different flow conditions, as we showing. So 90 degree is where the flow is perpendicular to the lines. 0 degree is essentially flow is parallel to the lines. And we look at two different particles, in this case, 250 and 500. And we look at two membranes. One is pretty shallow, about 100 nanometer tall, and the other is 170 nanometer tall. And you can analyze essentially the critical flux based on the shear-induced diffusion, and then back up the shear-induced diffusivity prefactor, right? So that shows you the larger this value, the more enhanced shear diffusion or back diffusion introduced by the pattern. That's the key message. So what we found essentially, as you can see that compared to the unpatterned membrane, these patterned membrane have promoted back diffusion. And the taller pattern, these empty symbols essentially have larger enhanced diffusion than the shallow pattern, okay? And the larger particles have essentially more enhanced diffusion than the smaller particles. Now we do believe, because of size differences of the particles, there are some other factors other than hydrodynamics, for example, like size exclusion, right? I showed you that for the 500 nanometer pattern, a 500 nanometer particle, it cannot fall into the trenches, right? So there can always be liquid going underneath it. And John, our collaborator, Pellegrino, and with other folks that has background in the CFD simulation that look at the shear stresses near the membrane surface. So this is the gradient shear rate. This is distance from the membrane surface to all the way into the feed. And you can see the shear stresses is enhanced by the patterns. And that degree of enhancement, so this is for unpatterned, and for patterned membrane, increase obviously with Reynolds number, essentially the flow rate. All these, again, just to confirm that you can enhance the hydrodynamics. Okay. And for the time limit, we also look at protein fouling. So where we compare the patterned and unpatterned membranes, right, using a multi-stage protein filtration of buffer with a BSA, and then buffer again, and a DI water wash. The key message is that you can see these pattern membranes when BSA is introduced have better performance or less fouling than unpatterned membranes. Okay. And this effect is independent of pH value that suggests it's universal due to hydrodynamics rather than due to protein absorption on the surface. And we look at the Tfc membrane as well. This is by John's student. Basically, we fractionated sodium chloride mixture with glycerol with BSA. Again, the key message is that if you compare the non-patterned membrane and with the patterned membrane, and if you mark where the flux declined by, to 92% of the original value as a marking here, and this is for essentially 1 day for the patterned membrane to decline to that level under cross flow. And for the non-patterned membrane, you get very quick reduction in flux. So, and lastly, we did reverse osmosis. This is unfortunately did it in a dead end stir cell because we couldn't make a very large kind of defects-free patterned membrane for high pressure testing. So we did it in a smaller sizes, but still, even with the stirred filtration cell, the hydrodynamics is not ideal compared to the previous slides, which I showed on the true cross flow. but you can still see sort of the unpatterned membranes that, this is a concentration polarization, the flux decline, and then salt precipitation that causes a flux reduction. The patterned membrane can reduce a little bit concentration polarization, and it reduces essentially the salt precipitates on the membrane surfaces. Okay. So this is essentially sort of a quick overview of what we have done with essentially direct patterning ultrafiltration membrane and Tfc membrane and their anti-fouling performance against different foulings. But as I mentioned earlier, that the imprinting methods that we just did, the thermomechanical methods, has a limitation because it doesn't work very well for if you want to pattern larger features like 5-10 micron structure, because of the mechanics. Okay, and also it's not good when the pattern size matches the pore size. Like if you want to pattern 100 nanometer features on top of 100 nanometer pores for microfiltration membrane, that doesn't work very well. And for those microporous membrane, I know a couple of talks will be focused on this symposium about membrane distillation. You want to use those microporous membranes. So recently, we essentially developing a new method, and I'll finish this in less than 1 minute. We put essentially a soft lithography, combining a soft lithography, make a PDMS templates, and it just cast in the dope solution, which is a PVDF mixed with a high boiling solvent polymer, squeeze them, introduce phase separation, extract solvent out, and you can make a patterned microporous membrane. Right? And here's a picture of showing, and the work is just recently published, patterned PVDF membrane with pore sizes about 500 to 600 nanometers. Right? So with that, I would like to conclude my talk. I hope that I showed you that we're now developing essentially new methods that can directly pattern UF by nano imprinting. And if you grow IP layer on top of the patterned UF, you can make NF or RO membrane. And if you combine soft lithography with conventional TIPS process, you can make MF type of pattern membranes. And these patterns can enhance essentially hydrodynamics and it can essentially leads to less fouling of proteins. And so far, we hope we have more, but limited evidence that you can even control salt precipitation in our desalination. Okay. So with that, I want to quickly acknowledge the people who have worked on these projects, the funding agencies, and our collaborators. Okay. So thank you very much.
Okay, great. Thank you for that very interesting presentation. Again, it's Zoom, so I guess only I can give you the applause. But yeah, since it's a small group, again, people can be watching from the outside, but the people that join the Zoom can be the participants. And since we do have these participants here, I would open up the floor just for maybe one question, because we're in the interest of time. So does anybody have a question? Maybe 2 questions? I could maybe start while people are thinking. There has been work, right, on scale up. I've seen these big drums that roll. Has it been successful work on the scale up, or?
As far as I know, so we patented this, and one of the small startup, and they got the exclusive license, and they're trying to do it. But honestly, from what I know, it's still a very challenging task. There are continuous row-to-row nano imprinting, but so far the focus was not on patterning membranes. The row-to-row nano imprinting, most of the cases are UV cross-linking. So you're casting a solution and you contact the pattern in a row-to-row fashion and introduce UV for cross-linking, but rather than using what we do with pressurization and heating. So definitely there are capabilities for scaling this up are being developed, but I would say in a row-to-row high pressure type of imprinting is still not there yet.
Okay, great. All right, so I suggest we move on because we started a bit late, but now the last session will be from 1/4 to 1:45. Thank you again, Professor Yifu Ding, and thank you for joining.
Thank you. Sorry for the delay.
No, it is the technical difficulties at the start. So let's continue now. I'd like to welcome Professor Jongho Lee from the University of British Columbia, Canada, and he'll be speaking on the design and applications of vapor gap membranes for water and resource recovery. So Professor Lee, if you could share your screen, and the floor is yours.
Okay, thank you, Chris, for the introduction, and also thank you for inviting me to this great venue. Okay, so hello everyone, my name is Jongho Lee from UBC. Today, as Chris said, I'm going to talk about vapor gap membranes for water and resource recovery. So as we know, the wastewater has been regarded as pollutants to treat, traditionally as pollutants to treat and remove, but wastewater is now more and more recognized as a resource because it contains lots of different chemicals, including organics and nutrients, or also the water to produce the water of different degrees, biofuels, electricity, biochemicals, fertilizer, and so on. So to transform such waste into these resources, the separation processes are essential so that those specific compounds can be extracted into these resources. So as you know from our previous talk, the membrane-based separation processes are widely used in water and wastewater treatment processes, as well as chemical separations. So in many membrane processes, typically the target compounds can be extracted or retained by size exclusion, or using the contrast in the rate of diffusion. But if the target compounds are volatile or gas species, this so-called vapor gap membrane, which is non-wetting porous membrane, can be more suitable or effective. And when this non-wetting porous membrane, and so-called vapor gap membrane, is immersed in liquid solutions, then this because of the non-wetting properties, the membrane pores can capture the air bubbles and form a vapor gap. So the liquid cannot penetrate into this pore, so only the gas species can move from one side to the other side, so that the target compounds can be extracted into permeable solution. So in that situation, by applying a suitable or appropriate driving force, we can specifically extract the target compounds from feed wastewater into permeate. For example, if a temperature difference is applied across this membrane, then it induces the water evaporation from the hot side and the water condensation on the permeate side, so we can recover the water. Specifically, this technology is called membrane distillation, and I believe Dr. Xiong will talk about this technology in the later session. And as a variant of this technology, this water flow can be even used to further generate electrical energy. And if the pH gradient is applied across this membrane, the ammonia present in the wastewater can be extracted into the permeable solution and used as a source for fertilizers. And also, if the solubility difference is applied across this membrane, then we can harvest the biofuel such as methane. So today I'm going to show a couple of examples of this using the vapor gap membrane to recover water and biofuel from wastewater. So first, the water recovery from wastewater using this vapor gap membrane is particularly important to treat industrial wastewater. So many industries, such as the major industries such as oil and gas industry, produce very highly saline wastewater. For example, the shale gas produced water, its salinity can go up to almost 300,000 ppm, which is way higher than the treatable limit by reverse osmosis. And also some industries such as mining, they are under huge pressure to minimize their wastewater discharge. So the technology that has to deal with the treat very highly saline wastewater. And for such industrial wastewater treatment, vapor organic membrane can provide a suitable approach. So in a technology again called the membrane distillation, this vapor organic membrane, the non-wetting porous membrane, is placed between the hot feed saline wastewater and the cold permeate fresh water. And then again, because of the non-wetting property, the only gas species, only water vapor can pass through this membrane. So this temperature difference creates a vapor pressure gradient across the membrane pores, which drives the water vapor from hot to cold side. Because this is a distillation process, the water flux across the membrane is almost insensitive to the salinity of the feed water, and also the salt rejection is very high because salt doesn't evaporate. And at the same time, the feed water doesn't have to be boiled as long as the temperature of the feed water is higher than the permeate solution. Water always goes through, water always moves from hot to cold side. So the low-grade heat, such as waste heat, can be used to heat up this feed solution to a moderate temperature. However, the problem is that the industrial wastewater has lots of different the contaminants, such as oil and grease, alcohol, and surfactant, which can reduce the surface tension of the wastewater. And such a low surface tension wastewater can makes a risk of wetting the hydrophobic or the wetting resistant membrane. So in the last the decade or so, researchers have worked on developing a vapor organic membrane, which is not only hydrophobic, but also omniphobic, meaning that the membrane can resist wetting against both water and other low surface tension liquids. And typically, these membranes can be fabricated by modifying the membrane surface texture, as well as surface coating using low surface energy materials. What we noticed from the recent studies of this wetting resistant vapor organic membrane is that when a conventional hydrophobic porous membrane is modified to get the higher wetting resistance, then the water flux is decreased. So if you look at this chart, this y-axis is the water flux after such wetting resistance modification divided by the water flux before the modification. So as you can see here, in all these studies, recent studies, once the membrane becomes omniphobic, the water flux was decreased from the previous flux when the membrane was just hydrophobic. So, so our question was whether there is any trade-off relation between the water flux and the membrane wetting resistance, and if so, what would be the potential cause? So to answer that question, we prepared different membranes that have different wetting resistances. We started with quartz fiber nanofiber membranes, and then we coated this membrane with 4 different silane, from the short chain alkylsilane to long chain fluorinated alkylsilane. So we can anticipate that these membranes have lower to higher wetting resistance from left to right order. So we prepared these 4 different membranes, and then when we measured the water flux across these 4 different vapor organic membranes in the membrane distillation experiment, we did observe that there is a trade-off between the water flux and the wetting resistance. So, so after we got these results, we thought about like 4 possibilities that could make this trade-off relation. Maybe the first 2 reasons we ruled out already, but basically, so maybe the membranes have different structures, maybe such as the fiber size, membrane porosity, or membrane thickness, or the membrane may have different thermal conductivities, But after we measured the membrane structural parameters as well as thermal conductivities, we didn't see any difference between among those 4 different vapor gap membranes. So as another reason, we thought maybe there are maybe those membranes have different liquid vapor interfacial areas for evaporation and condensation, or maybe those membranes have different effective membrane thickness, meaning that maybe those membranes have different gap distance between the feed side and permeate side liquid vapor interfaces. So to see the later 2 reasons are real causes, we used electrochemical impedance spectroscopy across these membranes. So basically, we sandwiched this membrane between the 2 electrolyte solutions, and we applied AC voltages with different frequencies. And the membranes can be modeled as a parallel circuit of capacitor and the resistor, because the capacitor can represent the air gap, the vapor gap between these 2 electrolyte solution, and a resistor. The resistor can represent any leakage of liquid across this membrane. So if we recall the classical capacitance, the formula for capacitance, the capacitance can be expressed using the effective area of the liquid vapor interface, as well as using the actual gap distance between these 2 solutions. So these are the normalized measured capacitance of those 4 different vapor gap membranes. And we added the surfactant to the electrolyte solution to gradually reduce the surface tension of those electrolyte solutions. And as you can see here, the membrane that has lower wetting resistances have a more rapid increase of the capacitance. Then if you look at this formula again, the capacitance increases when the interfacial area increases, or the effective thickness of the gap decreases, or both. So next, what we did is that we wanted to see whether this effective membrane thickness are actually different among those 4 membranes. So what we did is that we stained at the top surface of the membrane, each membrane, with fluorescence dye, and looked at the cross section. So in the left-hand side, these are the cross-section image of the highly wetting resistant membrane, and the right-hand side is showing the cross-section of lower wetting resistant membrane. And this green liquid is the fluorescence dye, and as you can see here, this green liquid does not penetrate into the membrane inside structures. So virtually those 2 effective thickness of the membranes are essentially the same. So from this observation, we concluded that those observed capacitance increase is due to the increased the liquid vapor interfacial areas. So this observation brings us to suggest the following mechanism. So when the wetting resistance of the membrane is very high, then the liquid vapor interface is formed at the top surface of the membrane. But when the wetting resistance is lower, is reduced, then that induces the sagging of the interface, so that the interface can touch the subsequent layer, which induces the expansion of the interfacial areas, so that the evaporative water flux is increased. So that was the major finding of this study. So just to summarize this first part, so of course it is essential to have the very highly wetting resistant membrane for membrane distillation applications. but a vapor gap membrane that has high wetting resistance likely has a reduced liquid vapor interfacial area, so the water vapor flux will be likely be reduced. And we also believe that so when the wastewater surface tension is not that low, and if the value of the surface tension is more or less consistent, then the wetting resistance of the vapor gap membrane can be tuned such that the higher water flux can be produced for a given the surface tension of the feeder water. Then let me switch a gear to the biofuel recovery using the vapor gap membrane, specifically biomethane. As we know, the methane is a very potent greenhouse gas, which is about 25 times more potent than the CO2. And currently, about 5% of the methane is emitted from the wastewater sector. So even though the methane is potent greenhouse gas, because the biomethane is major constituent of natural gas, if it can be captured, the methane can be a great source for energy. And in fact, in Sweden, more than like 80% of the natural gas vehicles are running on biomethane produced from wastewater or food waste. The conventional domestic wastewater treatment systems typically use the aerobic treatment process, such as activated sludge. In this activated sludge system, the aerobic microbes break down the organics into CO2, and the generated sludge can be anaerobically digested to produce methane as a potential energy source. But in this aerobic system, already more than 80% of the organics are already lost as CO2 because of the aerobic bacteria's activity. So if if the whole aerobic process can be replaced by an anaerobic process, we can actually convert most of the organics into CH4, the methane. So the anaerobic process has much higher potential to produce energy from wastewater. And at the same time, anaerobic process doesn't need aeration. So the energy cost for aeration can be greatly saved, which is currently taking more than 40% of energy cost in conventional wastewater treatment processes. The downside of the anaerobic wastewater treatment process is that it requires high temperature, such as 37 degrees C, because of the slower kinetics of microbes. But of course, it is impractical to increase the temperature of such a massive wastewater to such high temperature, such as like 37 degrees. So in the past decades, past 1 or 2 decades or so, researchers have worked a lot on the low temperature anaerobic treatment processes, such as upflow anaerobic sludge blanket or anaerobic membrane bioreactor. In this anaerobic treatment process, typically the biogas containing biomethane is collected in the head space. But as you can see from this graph, when the water temperature is reduces, the methane solubility increases. And typically in this kind of systems, the methane is super saturated in the effluent. So for example, at like 25 degrees C temperature, the more than 40 to 60% of the methane is lost as an effluent, as a dissolved gas. So that was our direct motivation to develop a system that can effectively capture such lost, dissolved methane, and so that the anaerobic treatment system can be more profitable. So So recently we proposed a membrane process called the solvent-based membrane contactor for SMC for dissolved methane recovery. So the operating principle of this process is quite simple. So basically, an omniphobic membrane, omniphobic vapor membrane is placed between the methane-rich wastewater and an organic solvent that has high methane solubility, low water solubility, as well as low vapor pressure. And then, because of the methane solubility, because of this organic solvent has a high methane solubility, the methane can be selectively extracted into the organic solvent, this drawer solution. But at the same time, because this solvent doesn't have high, and this solvent has very low water solubility, there is no water flux across the membrane. Then at the second stage of the separation, such as vacuum extraction, this recovered, this extracted, the methane can be further extracted into the fuel. So we tested this idea at 3 different temperatures, from 15, 25, and 35 degrees C. And this graph shows the methane concentration in the feed solution as a function of time. So as you can see here, when the temperature is lower, the initial concentration of methane in the feed is higher because of the increased methane solubility at lower temperature. And as time goes by, the methane concentration decreases. And at the same time, the methane concentration in the drawer solution increases. So clearly shows that the methane is moving from feed to the drawer side. And what's interesting here is that even when the methane concentration in the drawer is higher than the feed side, the methane still goes from feed to drawer side, which shows the advantage of this solubility-driven process for dissolved methane recovery. And at the end of this the process, we were able to observe the methane recovery more than 90% at all the tested temperatures. But this data is from the clean feed water that is basically distilled water saturated with methane, and we wanted to test actually actual wastewater that has a lot of solvents in it. So throughout through the collaboration with Dr. Jongho Lee at the University of Waterloo, we received actual anaerobically treated wastewater from anaerobic membrane bioreactor. Before this test, we were sort of expecting to see very bad membrane fouling and also very compromised methane transport property. But actually, when we tested this actual wastewater, we didn't see much difference. So in this graph, the black graph is from the methane saturated distilled water, very clean, no foulant feed water. And this red one is from the actual the wastewater that has very high foulant concentrations. And again, we didn't see any, virtually there is no difference between these two tests. So obviously we were very happy, but we were quite puzzled why this is too good to be true. So so after this test, when we opened our membrane cell, we didn't see any, virtually we didn't see much fouling on the membrane. So the membrane was still very clean. So it turned out that in this process, because there is no water flux across the membrane, so there's no convective flow that brings the organic foulant to the surface of the membrane. So that helped a lot to reduce the membrane fouling. So as a control experiment, we did membrane distillation experiment to produce the water flux across the membrane. And as you can see here, using exactly the same feed wastewater, we saw a lot of fouling on the surface. And throughout the several follow-up experiments, we concluded that this lack of water flux across the membrane helped actually prevents the membrane fouling in this SMC process. And finally, so we also looked into some energetics of this process to see whether this process can produce the net energy production. And in this graph, this is the energy that can be potentially produced by the recovered methane from 1 cubic meter of wastewater. And this blue bar is the energy harvest from such dissolved methane recovery. And the red bar is energy consumption. And then we compared with other two processes, including the just heating as a primitive way to give off the dissolved methane, and also vacuum membrane contactor, which is also sort of new emerging technology that people are looking into to recover the dissolved methane. And at the end of the day, we saw that after the analysis, we saw that there is a high potential of this process to produce the net energy from wastewater if that is combined with anaerobic treatment processes. So to summarize this part, so basically we demonstrated more than 90% of methane recovery, dissolved methane recovery at various temperatures, and we didn't see much fouling due to the lack of the water flux across the membrane. And again, we believe that this is one way to produce net energy from the wastewater, even at cold temperatures regions. Just to conclude, I hope I showed two examples of vapor-again membranes applications for water and energy recovery. But basically, if the non-wetting property is properly engineered and if it is operated under proper driving force, these vapor-again membranes have highly effective tools to recover water, energy, and biochemicals, and fertilizers, and so on from wastewater. So with that, I'd like to thank the lab members who worked on this, who did all these works, Xuesong, Abhishek, and Chansi, and also collaborators, Tizeng, Jahi, Hyungsu, as well as our industrial partner, Energia, and Fibercast, and also our funding sources. And with that, I'd like to finish, and thank you for your attention. I'd be happy to take any questions.
Thank you, Professor Lee. That was a really interesting talk. And of course, I'll give you the applause virtually. So yeah, because we have got a small group here, I'll open the floor for questions. Maybe I could start while people are thinking about your talk. You've got the draw solution, which is dodecane, right?
Yes, yeah.
So does that dodecane, does it also diffuse across into the water as your methane is diffusing across into the draw solution?
That's a very good question. So we deliberately chose dodecane because dodecane has very low vapor pressure, so it really doesn't evaporate. So we even tested we have even tested how much dodecane can be evaporated under vacuum. Then we put a beaker of dodecane under vacuum chamber for 24 hours, and then maybe it was less than 0.01% of the dodecane was evaporated even after 24 hours. So it was quite the suitable solution. But of course, if there is any other, better solvent that has higher methane solubility, that will be great.
Great, wow, thank you. Is there anyone else with the questions?
Hi, this is Shihong Lin from Vanderbilt. Thank you, Jongho, for the nice talk. I may have missed that, but how did you recover the methane from the drawer solvent?
Yeah, so we actually didn't yet. So the idea here is that we extract the methane here first into the dodecane, and then and then put the dodecane into the vacuum chamber to extract those dissolved methane. We didn't do that partially because the safety reason. So the methane, I believe that there is some minimum concentration for the explosion. I think it's 5% or something like that. So we initially wanted to extract the dissolved methane from the dodecane, but we didn't get approval for that test because of safety reason. But as I told Chris, the dodecane didn't evaporate really much, and then we believe that the methane can be extracted quite easily.
But then have you considered that in your energy calculation?
Yeah.
For the extraction?
So basically, the energy calculation here is consider the pumping cost for the liquid circulation as well as the vacuum extraction. So
okay.
Of course, the vacuum pump is much more inefficient compared to the case where the airflow is existing, but we consider that inefficiency into this calculation.
All right, thank you.
Okay, great. So I think that we will close this session now. I want to thank, first of all, the participants again for joining this session. And I want to thank especially the speakers who woke up early, if you're in Canada and the States, to deliver your talks. Thank you to Professor David Jasby, Professor Yifu Ding, and Professor Jongho Lee for giving the presentations today. So I'd like to thank everyone again. And I'd like to close the session. Another session on advanced functional materials and water treatment applications will be starting again in 15 minutes. Okay, thanks again. So I'd like to open the session now. This is the second session entitled Advanced Functional Materials in Water Treatment Applications. And again, I would like just to welcome everyone for joining this conference. I think there's even about 2,000 participants from all over the world. And I'd like to especially thank the invited speakers that have agreed to join us, also from all over the world. So it's, I guess, still in the morning in the United States for you guys, and in Europe. So I'd just like to start the session by just saying that advances in water treatment technology are supported by innovation in materials and exploration of non-conventional approaches to address the still unmet challenges are very important. We like to see these new ideas come to help with water treatment, solving the water issue in this Drylands Desert and Desertification conference. So we're a bit late because of these technical issues, but we'd like to start first with Professor Ranil Wickramasinghe. He's from the University of Arkansas, USA, and he'll be speaking on novel electrospun membranes for membrane distillation. So Professor Wickramasinghe, if you could share your screen, the floor is yours.
Thank you very much, Chris. And I just want to make sure, can everyone see my screen? Yes?
Yeah, I can see your screen. It's good now.
Perfect. Okay. So thank you very much for the introduction. And also, Chris, thank you very much for the invitation to attend this meeting. And actually, I was really looking forward to visiting Israel. And as you know, spending some of my sabbatical there, but hopefully this can be done in the future. But still, it's a great pleasure to be able to give this presentation. So my co-authors are Yuxuan Chiao, he's a postdoctoral researcher, and Jorge Almodovar, he is an assistant professor. We're all from the Department of Chemical Engineering at the University of Arkansas. And as was mentioned, I'm going to talk about developing fouling-resistant membranes that are electrospun for treating hydraulic fracturing flowback waters. I thought before I begin, I'll just tell you where we are. So I'm actually in Arkansas. I don't know if you can see my pointer, but Arkansas is in the south central part of the United States. And we are from Fayetteville, which is the northwest corner of Arkansas. So we are very close to Oklahoma, Missouri, and Kansas City. And probably the important thing about our Department of Chemical Engineering is that we lead a membrane center, a rather old membrane center called the Membrane Science, Engineering, and Technology Center, or MAS Center. It's a National Science Foundation Industry and University Cooperative Research Center that has about 20-odd industrial sponsors, and it consists of 4 university sites: ourselves, Penn State, University of Colorado at Boulder, and New Jersey Institute of Technology. And the work I'm going to talk about here, dealing with hydraulic fracturing flowback water, actually many of these projects start in the center or have had links with the center. This one actually started off with one of our sponsors, and more recently we've developed a collaboration with the Membrane Center in Taiwan, and so it does include some collaborative work with them as well. So the bottom line, which everyone knows, is that water is a very valuable natural resource, and therefore it would be great to be able to recover and recycle and reuse water. And oil and gas production actually results in a lot of co-produced, or what's called produced water, which is a wastewater stream that typically the oil and gas companies treat as a wastewater stream and would like to get rid of. They really don't have that much interest in water as a product. Recently, in the last 10 years, rapid growth in hydraulic fracturing operations has led to the recovery of oil and gas from so-called tight rock formations or highly impermeable geological formations and shale formations. And this has been enabled by the development of new technology, but the problem is that the hydraulic fracturing flowback and produced water is highly impaired. In particular, it has very high TDS, often total dissolved solids more than 100,000 ppm. It has dissolved polar and non-polar organic compounds, as well as surfactants and low surface tension foulants. And up to about 15,000 cubic meters of this water can be produced per well during development and stimulation. So today in the US, this water is generally trucked to an appropriate geological site where it can be re-injected into the ground. And it's important to choose these geological sites such that you don't impair any other water bodies, because the water in these other water bodies could be used for agricultural purposes and so forth. So the disadvantages: firstly, deep well injection is obviously costly because you're trucking water all over the place. But more importantly, it leads to earthquakes. And in fact, when I first moved to Arkansas about 10 years ago, I was surprised that we used to have occasional earthquakes, which is very rare in Arkansas. It's a geologically very old and stable area. And the reason is that there used to be a lot of hydraulic fracturing going on in what's called the Fayetteville Shale, which is in central Arkansas. Today, that has stopped to a great extent because of low oil and gas prices, but it can start up again whenever gas prices go up again. I just got a message saying somebody wants to enter the room. I'm just going to ignore that, right? Okay, so when you treat hydraulic fracturing flowback water, typically there are various levels of treatment. It's not just one step, it's a number of different steps. So primary treatment, which is typically something like gravity separation or centrifugation, is for deep well injection. So basically one skims off the oil that's on the surface and then deep well injects into some sort of geologically isolated formation. Secondary treatment goes a bit further. The idea is to treat the water sufficiently to re-inject into existing wells or new wells to stimulate new wells. And the problem is that this water contains fracking fluids and other things that cause corrosion of equipment. So typically things like coagulation, flocculation, filtration, electrocoagulation are used to treat the water somewhat more. And then tertiary treatment refers to basically evaporation, distillation type processes, if you want to actually treat the water and discharge into lakes and rivers. Shown here then is a schematic representation of the process. As you can see, there is a well that's drilled deep into the Earth's surface up to 1 kilometer in depth, and it reaches this shale-bearing or gas and oil-bearing shale formation that is very impervious. And the drill is then turned horizontally and can go for another up to 3 kilometers in length. High pressure water is then injected into this well, which contains a number of additives, things like fracking fluids, viscosity modifiers, and what's called proppant, which are these particles, basically sand. This fractures the formation, the sand goes into the fissures and prevents collapse of the fissures when the pressure is released. The pressure is released, and hydraulic fracturing flowback and co-produced water, as well as oil and gas is recovered, and it's treatment of this co-produced water that is a major issue. So we look at membrane distillation. Membrane distillation is a thermally driven process. The feed which comes out of the earth at an elevated temperature would flow on one side of a membrane, while the distillate flows on the other side, and the membrane is hydrophobic. This is called direct contact membrane distillation. And since the membrane is hydrophobic, only water vapor should transport through the membrane pores. The driving force for separation is the vapor pressure difference between the hot feed and the cold distillate. And so one doesn't need to boil the whole feed like conventional distillation. As long as there's a vapor pressure difference, this process will continue. One of the advantages of membrane distillation is if we look at this graph here, the vapor pressure of water versus, in this case, it's brine concentration or sodium chloride concentration, you can see the vapor pressure decreases with increasing brine concentration, but the decrease is relatively minor compared to, say, the increase in back pressure in a reverse osmosis process. And so there is still a significant driving force even at high brine concentrations. So this is our experimental setup. We have our produced water and our feed on one side of the membrane, and the distillate is collected on the other side of the membrane, and we are wanting water vapor to transport through a hydrophobic membrane. It's important to remember that non-volatile components such as dissolved salts will not transfer, so they will be concentrated in the feed reservoir. However, volatile components like ammonia will transfer and will be recovered in the permeate stream. And so obviously this could not be used to produce drinking water. Now, commercially available hydrophobic membranes today, like PVDF and PTFE, unfortunately foul during membrane distillation. And the reason is that the feed not only contains dissolved salts, it also contains polar and non-polar organic compounds, as well as surfactants and what's called low surface tension compounds. So these compounds can absorb on the membrane, foul the membrane, and eventually lead to wetting and passage of water directly from the feed to the permeate side. In fact, it has been shown that coming up with omniphobic surfaces, which have low surface energy, by itself may not be sufficient, because surfactants and low surface energy compounds can still absorb and will lead to fouling of the membrane. So ideally, one would want to have a so-called reentrant structure, which includes a kinetic barrier to adsorption. So that's the motivation for looking at electrospun membranes, which have this reentrant structure as possible membranes for membrane distillation. So in this work, I'm going to talk about basically three different membranes. So the first one is base PVDF. So we spin PVDF membranes, and we have these nanofibers. So that's shown by the first figure on the left-hand side. The second one is called Pvdfcf. So this is a PVDF. Into the dope, we have added a quaternary ammonium surfactant. So the PVDF contains positive charges in the dope solution. So we spin this, and then we modify the surface by growing silica particles by electrostatic interaction using dip coating. We then fluorine coat it, and so we end up with an omniphobic surface that has a low surface energy. And this surface is going to face the permeate. And then the final membrane is our bilayer membrane. So we have PVDF on the top and PVDF with our surfactant CTAB at the bottom. The bottom layer has been coated with silica and fluorine, but now we modify the top layer, which is going to face the feed stream. And we do that by alkaline treatment and then grafting Zwitter ions from the surface. So the top layer now has a hydrophilic layer next to the membrane, and this is the surface that's going to face the feed stream. So it should reject oils. It should not allow oils to adsorb and should be oleophobic. So let me show you some surface characterization data. Shown here are various contact angles: water, ethanol, and oil in water contact angles. So if you look at the water contact angles, this figure A, you see the PVDF and the Pvdfcf membranes have very high contact angles. They are hydrophobic, as would be expected. And the Pvdfbz membrane, which is the one where we grafted the Zwitter ions from the surface that faces the feed stream. If you measure the contact angle on that surface, it's very hydrophilic, as you would expect. If we look at the ethanol contact angle, for PVDF, ethanol actually wicks and passes through the membrane. The Pvdfcf membrane has a low surface energy and a relatively high contact angle for ethanol, but the Pvdfbz membrane, where we look at the hydrophilic surface, actually has a very low contact angle, which you would expect. If we look at the underwater oil contact angle, which is actually more realistic, because that's really what will happen during membrane distillation, the PVDF and Pvdfcf membranes actually have fairly low contact angles. So PVDF is hydrophobic. We were not surprised about this. And the Pvdfcf is probably due to hydrophobic interaction between the oil and the membrane surface. But what's important is the hydrophilic surface of the Pvdf-BZ membrane has a very high oil in water, underwater contact angle. So the hydrophilic hydration layer that is next to the membrane actually protects it from adsorption of oils. We conducted IR spectroscopy to make sure that we have actually modified these membranes as we would hope. Shown here are the IR spectra for the base, the PVDF, and then the Pvdfcf membrane. We're looking at the modified surface, and the Pvdf-BZ membrane, where we look at the hydrophilic surface. And basically, one sees that there are peaks at about 1402 and 1070 reciprocal centimeters that correspond to C8 stretching and CC stretching, and that's going to be there for all the membranes. What's mainly significant is that for the Pvdf-CF membrane, we have a very, very small peak around 1110, which is due to silanol because we have silica particles. And for the Pvdf-BZ, we have a very small peak around 1020 due to sulfur, which comes from our Zwitter ion that we grafted from the membrane surface. We also measured the zeta potential of the base PVDF and the PVDF membrane containing CTAB, and you can see that the zeta potential is much more positive for the dope that contains the quaternary ammonium surfactant, which is what we would expect. So then these are some SEMs of the nanofibers that we spin. So you can see the image A is the PVDF nanofibers that we have spun. Image B is the Pvdfcf nanofibers, and you notice they are a little bit thinner than the PVDF fibers. This is actually because these fibers contain the quaternary ammonium surfactant, so they've got a positive charge. So we had to use actually a higher voltage to spin them, which is why they end up being a little thinner. If you look at the inset at the bottom left-hand corner, you can see the silica particles that we grew from the surface of the membrane. And then finally, image C is the Pvdf-BZ fibers, the top surface, and the little dots are actually the Zwitter ions that we have grafted from the surface of the fibers. So let me move on to some membrane flux data now. And so if we look at the flux data, this is water flux for a synthetic solution. It's a DI water containing 3.5 weight% sodium chloride. And actually, these fluxes for all the membranes are generally much higher than you'd get from non-electrospun PVDF membranes. So the electrospun membranes are very, very porous. The water flux for the PVDF membrane, base PVDF, is the highest. Pvdfcf is lower, probably because we have smaller fibers, smaller diameter fibers, so the pores are probably smaller. And the Pvdf-BZ is slightly higher than the Pvdfcf, probably because we have that hydrophilic layer that faces the feed stream. Let's now look at some actual performance data. So firstly, we wanted to check the anti-wetting properties of the membrane. Remember in membrane distillation, we don't want the membrane to wet. If it wets, we're going to get water transferring from the feed to the permeate side, and then the whole process basically ends. So if we look at figure A, we have here on the left-hand side y-axis the normalized water flux. So we normalize all the fluxes with the flux we got for that membrane in the first 10 minutes. The bottom x-axis is time, and the right-hand side y-axis is a rejection of salt. So the feed stream was again 3.5 weight% sodium chloride, but in this figure A, we added SDS. And the top y-axis gives the SDS concentration. So we start off with 0 SDS, so all we have is 3.5 weight% DI water, and we run for the first 2 hours in membrane distillation. And you can see for all three membranes, the flux remains about 1, the normalized flux. So there's no decrease in flux, no fouling or anything as you would expect. And the rejection for sodium chloride is very close to 99.78%. So it's very high. We then add 0.1 molar SDS. And what you notice is that these open triangles, which represent the flux for the PVDF membrane, suddenly start to increase rapidly, and the corresponding rejection given by the open red squares decreases rapidly. So we have breakthrough. So we have wetting of the membrane when we add SDS as surfactant, and we have immediate wetting of the PVDF membrane, and the membrane fails. What you notice is that the modified membranes, whether they be the Pvdfcf or BZ, both actually are resistant to wetting by SDS at these concentrations. We increase the concentration all the way up to 0.4 millimolar. And the flux remains approximately constant at 1, the normalized flux, and the rejection remains constant also. We then wanted to look at anti-fouling, again using a model feed stream. So this is 3.5 weight% sodium chloride, to which we added 1,000 ppm crude oil. Again, normalized flux on the left-hand side. This is figure B, y-axis, and time is at the bottom in hours, and the right-hand side y-axis is the rejection. So you can see what happens. For the PVDF and the Pvdfcf membranes, you see the flux starts to decrease almost immediately and relatively rapidly. Soon the normalized flux is very, very low. It's almost zero. The PVDF-BZ membrane, which has that a very strong hydration layer due to the presence of our graft and zwitterions, actually resists fouling or adsorption of oil. And you can see the flux does decrease, but much, much more slowly. So the productivity of this membrane is much better. We get much more water that we can produce, treated water. And importantly, the rejection of sodium chloride for all membranes remains approximately constant and very high. So adsorption of oil will not lead to breakthrough of water, but it will lead to fouling and decrease in flux. So finally, we put both together. We put SDS and the mineral oil together in the feed stream containing 3.5 weight% sodium chloride. So what you see is here, again, normalized flux in figure C on the left-hand side y-axis versus time is the x-axis, and the right-hand side y-axis is rejection. So what's most interesting is a PVDF membrane. If you look at the flux, it's these open blue squares. You start off at a normalized flux of 1. There's initially a slight decrease in flux for about the first 30 minutes, and then suddenly a rapid increase. And if you look at rejection given by the red squares, initially there's a constant rejection, very, very high, close to 100%, and then it suddenly drops after 30 minutes. So what happens is first oil starts to adsorb, it starts to lead to fouling, you get a decrease in flux, but at the same time SDS is also adsorbing, and so very soon you get wetting and breakthrough and the membrane fails. For the two modified membranes, you can clearly see the rejection for sodium chloride remains high at close to 100%, but you see a definite decrease in flux, and it is much more pronounced for the CF membrane. So again, the BZ membrane, when you have that hydration layer, is resistant to fouling by oil, which leads to a much higher flux and productivity of water. So finally, we tested these membranes with the real produced water that we obtained from a commercial facility. The real produced water is far more complicated. As you can see here, here are some of the water analysis parameters. The TDS was very high, 245,000 ppm. It has dissolved organic compounds. The total organic carbon is about 120 milligram per liter. It has suspended colloids and other particulate matter, 131.1 milligram per liter total suspended solids. And then you can see the various major components, inorganic components that are present in this produced water. So we challenged our membranes with this produced water. So figure A at the top is what happens with the PVDF membrane, normalized flux on the left-hand side, cumulative permeate volume is the x-axis, and conductivity of the permeate, which is a measure of rejection, is on the right-hand side y-axis. And you see immediately you start to get a decrease in flux during fouling, but you're also getting an increase in conductivity, which means you get fouling, significant fouling, but you're also getting water breaking through the membrane pores. The PVDF-BZ membrane is shown next. That's figure C, shown in the bottom left-hand corner. And you can see the conductivity starts to increase slowly, but it remains below 50 microsiemens per centimeter. And we generally consider conductivities above 50 microsiemens per centimeter as being the case when we have breakthrough of water and the membrane fails. And you can see the flux continues to decrease slightly. If you look at the CF membrane, the performance is very similar. Again, a low conductivity that increases slowly. The flux decreases, actually the flux decreases much more than for the BZ membrane, and the initial flux of the BZ membrane was higher anyway. So having that hydration layer is very important to prevent breakthrough and adsorption of oil on the membrane surface. I would also say that one of the things we learn is that we need to regenerate the membrane at some point, and regeneration typically is flushing with DI water. And if the membrane fails and you get water passing through, regeneration becomes very difficult. So you have to regenerate before you get breakthrough of water in the membrane. So I think I'm almost out of time. So let me conclude by saying that we've developed a novel bilayer electrospun membrane consisting of both PVDF and PVDF nanofibers containing a quaternary ammonium surfactant, CTAB. The PVDF nanofibers containing CTAB were modified, that surface that faces the permeate stream, by graft of growing silica nanoparticles and putting fluorine for a very low surface energy omniphobic surface. The PVDF nanofibers that face the feed stream were modified by making them hydrophilic by grafting a zwitterionic polymer from the surface, and the membrane was challenged with a rather impaired produced water, and we found that the excellent fouling and wetting resistance. What we show here is it's essential to tune surface properties based on feed and permeate conditions. I also pointed out at the start of this presentation that this is typically a number of unit operations. It's not just one. So coming up with more robust and stable electrospun membranes means two things. Firstly, this might be viable because the membrane doesn't fail. You can actually produce enough water before you have to stop and regenerate the membrane, but also it might reduce the amount of pretreatment required, which is also, of course, help make this a more sustainable process and commercially viable process. Electrospun membranes contain reentrant structures providing a kinetic barrier to absorption of low surface energy compounds such as surfactants, which is very, very important in this application. And finally, I'd like to acknowledge funding which has come from the National Science Foundation, the University of Arkansas Chancellor's Fund, and also for the collaboration with the R&D Center for Membrane Technology at Zhongho University in Taiwan. Thank you very much for your attention.
And thank you, Professor Wickramasinghe. That was very interesting, and because it's it's a online conference, you can't hear the applause, but we all appreciate it very much.
Thank you very much.
So the participants who've joined the Zoom meeting have a chance to ask questions. And since there are a limited number of participants, I'll let the participants ask questions themselves. I could maybe start just by asking just about the regeneration. You know, I noticed that in the PVDF membranes, there's a very sharp failure point. So you would be able to maybe regenerate before that sharp failure point, but the other membranes had a little bit less sharp. So where would you regenerate, or can they be regenerated kind of as it gradually?
Yes. Very good question. So yeah, the PVDF, there is a sharp point, so you'd have to regenerate before you get to the point. The important point here is that if you have adsorption of oil, you can generally flush with water and try to remove some of that. You'll always start off again with a lower flux, but you can keep regenerating this way and using the membrane a number of times. If, however, you get breakthrough and you get water passing through the membrane pores, regeneration is almost impossible in a practical sense. I mean, using online regeneration in place is almost impossible. So that is one of the challenges, that with these membranes where basically what you're seeing is slow fouling with time and therefore lower and lower flux. Sometimes you actually don't get breakthrough at all. All that will happen is the whole thing will plug. That is also bad because then regeneration is bad. So part of this is, and what we're working on now is trying to find the optimum point for regeneration. And basically, it's probably going to be based on like a certain percentage of the initial flux. So if you get to maybe 50% of the initial flux, you stop, you regenerate and start again. And there'll be an optimum point, and then you can keep using this for a certain number of cycles. And then that's probably the end. So yes, regenerate. And it's difficult to regenerate also because the feed is so complex that you don't actually want to change the properties of the surface too much. So basically it's just DI water or some sort of water that tends to be the easiest and most effective way for regeneration.
Right, great, thank you. Are there any other participants that want to ask a question?
Yeah, I'm Professor C.N. Murthy from Baroda, India. Hi, Professor Wickramasinghe. A nice, interesting talk.
Thank you. I think, have we met before or not?
Yes, sir. You had come to Baroda.
That's what I thought. I thought we had met. Yeah, I just found you. I was trying to see where your video was. Okay, I just reached it.
Okay,
yeah.
I just start my video. I put on my video. You can see me?
Yeah, I can see your name. But that's okay. Go ahead with the question, please.
Yeah, actually, interesting talk. I just wanted to know what is the temperature difference between your hot end and the cold side, and is there any temperature effect on the flux?
So firstly, to answer the first question, we artificially maintain this at 60 degrees and 20 degrees Celsius on the two sides.
Okay.
From a practical application, this is actually quite tricky because people always say, you know, the water is coming out hot, so membrane distillation, you save on separation cost. But I pointed out that there are a number of processes. It's not just straight, you don't get your water straight out of the ground, take your oil and run it into a membrane distillation, you foul the whole thing. So there's pretreatment and so forth. So actually, how much of that energy you can recover for your separation is uncertain. Okay, I'm not sure how much can be really recovered. So ultimately, there's a separation cost. Now, the people that we worked with were actually producing natural gas. So for them, the energy cost wasn't such a big concern because as far as they were concerned, their product was gas. So if you need to use natural gas to, you know, run a reboiler, that's okay. That was the first part. The second part you asked me was about temperature. So temperature difference is important. A couple of things are important here. As you can imagine, as you start to, I didn't talk about it here, as you start to concentrate the feed to very high concentration TDS, you're starting off very high as well, right? You can get crystallization and precipitation. And so one of the processes we are coming up with actually is having a lower temperature in the feed tank and then heating before we send it into the module so that we try to get scaling precipitation within the feed tank. So the temperature difference does have a definite effect on this. Clearly, it affects it when you're close to the saturation limit and the risk is there of getting scaling. That's one effect. The temperature effect in terms of having a higher temperature, so therefore a higher vapor pressure difference also, of course, exists. That also is there. And using higher temperatures, of course, would speed up the process. That is probably at the moment less of a driving force because there's an energy penalty to pay for that as well. But the bigger one is because we're working with such high TDS waste streams, typically well over 100,000. The bigger issue is controlling the temperature of the feed tank and preventing scale formation.
Okay, thank you.
Thank you.
Okay, great. So thank you again, Professor Wickramasinghe. Thank you for your talk. We'll move on to the next talk. The next talk is from Professor Shihong Lin from Vanderbilt University in the United States, and he'll be speaking on material strategies to overcome fouling, wetting, and scaling in membrane distillation. So another related talk. And Professor Lin, please, the floor is yours. I think you're on mute.
Can you hear me now?
Yeah, we can hear you now. Yeah.
All right, can you see my screen?
Yeah, it's all good.
Yes. All right. Thank you all very much for inviting me to this really exciting event. Actually, I think that thank you, Renew, for doing a lot of the great introduction to MD. And actually, I think a lot of the stuff that you talk about would kind of be mentioned here. But this talk would, I would not talk much about like the details in fabricating material and all that, but rather on the more fundamental principles of how like certain types of material can actually address certain problems in MD. So because MD has already been talked about like in 2 talks today, so I'm not going to talk about how it actually works. So I will skip this, but I will briefly talk about the 4 major configurations in MD. So one is called direct contact MD, where you have the hot solid stream and the cold distillate stream both in contact with the membrane, which is the most typically studied in literature, but not actually, but it's not necessarily the most promising configuration in industrial application. Now, this one, from what I heard from the experts on scaling up and all that, is the most promising one, which is called air gap MD. So basically, here you have the this is the feed stream, the hot solid stream, and then you have a membrane, and then you have a small air gap. And on the other side of the air gap, you have the condenser. Like think of this as like aluminum plate, and then you have cold water going through. This cold water is not necessarily, it's not the distillate, but can actually be the feed water as well after it cools down. So the distillate actually forms on this side of the condensate plate, and then it's collected as a separate stream. And then the next one is called sweeping gas MD. Basically, instead of using water to collect the distillate, you just like blowing air through this channel and collect all the basically the humidity inside this channel and condense it in an external condenser. The last one is similar to the third one, which is called vacuum MD. Instead of blowing air through the channel, you're actually using vacuum to suck it out. And one advantage compared to this is that you actually create a larger driving force because of the vacuum, but you're going to cost more energy as well. So these are the several configuration of MD. Those sweet spots for MD, I think Renew has kind of mentioned that as well. So first is when the feed salinity is too high for reverse osmosis to treat, right? So as long as reverse osmosis is capable of doing the job, probably thermal distillation is not the way to go because it's usually more energy intensive. But there are places where reverse osmosis would not be able to excel, and that's where thermal distillation may play a role. And then when we have abundant low-grade waste heat available, so this heat are like relatively low-grade, and if you're not going to use that, you're going to waste that anyway. So in that case, the energy consumption may not be very low, but the energy cost can be quite low. And so fracking wastewater desalination, just as Renew talked about in his presentation, is actually one really sweet spot that combines both of these two characteristics. Now, so let's just very briefly review what this membrane serve. This membrane actually serve as, so the membrane distillation by definition, right? So thermal distillation using a microporous and hydrophobic membrane. So it has to be microporous because the membrane actually serves as a medium for vapor transfer, and it has to be hydrophobic because the membrane also serves as barrier for direct liquid transfer. So these are the two major functions the membrane serve. So there's three major mechanisms by which the membrane can fail. The first is called wetting, right? So here some of the pores are actually penetrated through. So it's bad because now the salt rejection would go down, and so it's no longer doing the desalination. The second very important mechanism of fouling, especially for treating very saline water, is the mineral scaling. So once the water is concentrated to beyond a certain extent, then the salt would basically precipitate on the surface of the membrane. The consequence of that was the water flux would drop because now you have some blockage, but also it may possibly lead to wetting and even pore damage because of the crystallization pressure. So this crystal, when they crystallize within the pore, they can probably damage the membrane. Lastly is fouling. So when you have organic fouling, hydrophobic fouling, like for example, oil, then it really like to adhere to the hydrophobic membrane and thus clog the membrane. So the obvious consequence is basically water flux decline. So how do we actually address these challenges in membrane distillation? So I'll talk about each of them and mostly focus on the fundamental mechanisms. So first of all, fouling. Fouling, I would say, is the relatively simple problem to address in the sense that it's a very common problem to all membrane processes. So in all other pressurized filtration processes, you have the problem of fouling, right? So people have been studying this for many, many years, like decades. So the basic strategy is usually to have a composite membrane where you have a hydrophilic layer on the surface that is touching the feed water, and this hydrophilic layer is usually underwater oleophobic. So people have done something like that in many, many other membrane processes, and it usually appear to be effective. So this is one of the early example back in membrane distillation back in 2016. So basically here we're coating a PVDF membrane with a layer that is very hydrophilic. And as you can see here, is underwater really oleophobic, and it gives a really good performance in terms of resisting the fouling by an oil water emulsion. So this is a PVDF membrane, and this is the coated membrane. So in terms of principle, fouling resistance is relatively simple if you have a relatively simple fouling agent. But if you have like very complex fouling agents such as biological fouling or humic acid, things are getting more challenging. And actually this problem has not completely been resolved even in other more mature pressurized filtration processes. Back in 2016, we also introduced a method called oil probe for spectroscopy. So the idea is really very similar to AFM, but instead of using a colloidal probe, you just use a droplet of oil as the probe. And so you're trying to approach the surface of the membrane and then contact it and then retract it. Now, I'm not going to go through the details of the process, but I just want to point out two things here. So if the membrane is attractive to the oil droplet, then upon the contact, which is this point here, you see a sharp jump of the adhesion force. So this is one thing. The second thing is that if the oil actually adhere to the membrane strongly, then when you retract the probe, which is this part of the curve, eventually the droplet would split and part of that would remain on the membrane. And you see basically a difference between the original baseline and this baseline after the retraction. So this difference is due to the portion of oil that is retained by the membrane. So this curve is for the PVDF membrane. As you can see, the feature that I just described, right? The very strong attraction. Sorry about that. Very strong attraction upon contact and some retention of oil droplet. Now with the composite membrane, you don't see either of them, right? So there's no attraction upon contact, and there's very little retention of the oil droplet on the membrane, and that's due to basically the hydrophilic layer would form a hydration layer, which would create a barrier for the oil adhesion to the hydrophobic surface. So that's fouling. Now wetting is a little more interesting because this is a problem that you do not see in any other membrane processes, except for like membrane contactor, which is basically a cousin of membrane distillation. In all other pressurized filtration processes, I mean, the liquid would go through the membrane pores. Okay, so first of all, I would like to talk a little bit about how we actually detect wetting. So there are three stages of wetting. The first stage was when the membrane is like completely unwetted, right? So there's no infiltration of any liquid into the pore. And then you would go through this transition state where part of the liquid actually enters the pore, but it does not fully penetrate through the pore. And the last stage is when you have like liquid penetrating through the pore, and if that happens for the entire membrane, the membrane would actually become translucent. So conventionally, the way to measure wetting is to just measure the conductivity of the distillate. So if there's any salt in the distillate, the conductivity would just goes up. But the limitation with that approach is that you will not be able to detect anything that is happening in this transition state when none of the pore has been fully penetrated, but a lot of the pore has already been partially infiltrated. So more recently, people developed two methods, one from our group and the other from a European group. So one method is based on this single impedance spectroscopy. Basically, we're measuring the impedance across the membrane. And so even though the gap is not conductive, but it serves as a capacitor, which under AC voltage, you can actually measure its impedance. So with that approach, you can actually measure this transient behavior of wetting. Another approach is actually based on optical. It's an optical approach where basically you measure the intensity of the transmission of the membrane, which actually takes us move a step forward because now you can have spatial distribution, spatial information about the distributed wetting. So the mechanism of pore wetting is based on this really old theory that there is a liquid entry pressure, which is basically the minimum hydraulic pressure that you need in order to push the liquid into the pore. And this value, liquid entry pressure, depends on the surface tension of the liquid, the surface energy of the material, and also the geometry of the pore. So the very simple criterion is that the hydraulic pressure is larger than the liquid entry pressure. Now, there are two types of wetting agents that may induce wetting. One is like, for example, water mixable low surface tension liquids such as alcohol, and another type is surfactant, they behave very, very differently. And some people believe that surfactant absorb onto the membrane and make the membrane hydrophilic and thus induce wetting. But we actually have a series of studies proving that is not the case, actually. So in both cases, the wetting is still basically complies with this simple criterion of basically comparing the hydraulic pressure difference and the LEP. I'm not going to go into the details of that, but basically whether you have an alcohol-induced wetting or surfactant-induced wetting, even though their behaviors are very different, but they still comply with this criterion. So how do we actually mitigate wetting? So here comes the importance of reentrance structure, which Renu mentioned in his talk. So what is a reentrance structure, right? So if you look at a cylindrical pore, which looks like this, if you have a low surface energy of the material, then you can resist wetting or the infiltration of the liquid if the liquid is has a high surface tension, such as water. But if you have low surface tension liquid, then the water would basically, the liquid would basically penetrate through into the pores. Now we need reentrance structure, which is structure where basically the opening of the pore is actually smaller than the opening when you enter deeper into the pore, right? So the idea is that you want the water-air interface to actually expand as the water-air with the water intrude into the pore. So that's basically reentrance structure. The idea, the fundamental mechanism behind why reentrance structure is actually wetting resistant is that if you have a low surface tension liquid with a conventional long reentrant pore, basically the free energy of the system would decrease as the water-air interface propagate into the pore. However, with a reentrant structure, because of the expansion of the water-air interface, you would actually have a energy barrier. Basically, you have a metastable state for the non-wetting state. So here, in order to overcome this energy barrier, you have to apply a large enough pressure. So that's why even with low surface tension liquid, which is thermodynamically well, in which case the wetting is thermodynamically favorable, you can still maintain a non-wetting state that is metastable. So the first omniphobic membrane for membrane distillation was reported in 2014. This was based on one of my work when I was at Yale. So basically, instead of using this really strange structure that you can only make using photolithography, you can actually use some nanoparticles to create this reentrant structure locally and reduce the surface energy of this nanoparticles and achieve this omniphobicity. Now, later on, there are many works on making omniphobic membrane, and this is actually one example from one of our speakers today, Jongho Lee. So as you can see here, so this is a conventional hydrophobic membrane. So it resists wetting by high surface tension liquid, but not low surface tension liquid. While an omniphobic membrane is resistant to basically liquids of all surface tension. And so if you add like surfactant when doing membrane distillation for conventional membrane, you would get wetting very quickly. While for omniphobic membrane, you can maintain the performance for a really long time, even at low surface and tension liquids. So more recently, people are looking into not using nanoparticle modification, but just using conventional hydrophobic membrane, commercial hydrophobic membrane. They realized that a lot of the hydrophobic membrane, commercial hydrophobic membrane, they actually have reentrant structure. The reason why they are not omniphobic was because their surface energy is not low enough. So for example, this paper from Professor Tong's group in Colorado State, they basically use conventional hydrophobic membrane and try to etch the membrane and then put some very long chain floral molecules on the surface, and they can actually achieve omniphobicity as well. So this gives a way to basically scale up fabrication of this membrane without doing something that is very complicated, such as like nanoparticle coating also. So, but what I want to point out is that amylophobic membranes are actually not underwater oleophobic. So the idea is that amylophobic membrane, they still have low surface energy, right? So even though the reentrance structure would prevent the oil from, or any low surface tension liquid from entering the pore, but they would still try to spread on the surface of the pore. While in the case of hydrophobic membrane, you actually have wicking, so the oil would actually enter the pore and just like clog all the pore. So we use the oil profile spectroscopy to compare these two cases, one with amylophobic membrane and the other with hydrophobic membrane. So as you can see, the black curve is for the PVDF membrane. I explained the two features, right? So as you, before, so one is the adhesion upon contact, and the other is the retention of the oil droplet upon retraction. So with the amylophobic membrane, you will still see this attraction. You see this adhesion upon contact. But when you pull the oil droplet back away from the membrane, you will see that very, very little oil droplet actually retain on the surface of the membrane, because they actually level wick into the pore. So this is more, the fouling is more reversible. Nonetheless, with either membrane, you will still have fouling, right? Because fouling is basically just clogging of the pores of opening by the fouling. In this case is the oil. So amylophobic membrane is actually not anti-fouling. Now, so in order to create an anti-fouling membrane, you need to have this basically genus O membrane, which is basically very similar to what Renew just talked about, right? So you want to have an amylophobic substrate and an hydrophilic surface, right? So this combination of the two features would give you a membrane that is both anti-fouling and anti-wetting, right? So we make such a membrane used by modifying commercial membranes back in 2017. Well, so this is the bottom of the composite membrane, the genus membrane, which is amylophobic. And then this is the top of the genus membrane, which is basically hydrophilic and oleophilic. But as you can see here, even though the water, the contact angle for the liquids are very low, they do not actually wick into the pore, because underneath this hydrophilic surface, they actually have a amylophobic substrate that would prevent the wicking. So similar to what Renew just reported, here you can see that such a membrane is really good for wetting resistance and also fouling resistance. All right, so that's what we have for wetting. Now, lastly, mineral scaling is actually, I would argue that is probably the most important problem to address, because other problems, sometimes you can do extensive pretreatment to remove the foulants, and for wetting, you may not always find like wetting agents in your feed water. You may find that in some water, but not necessarily in all feed water. But mineral scaling, if you're going to use MD for zero liquid discharge, or trying to push the water recovery to a really high value, then most likely you would have mineral scaling. So there's some mechanism for basically nucleation, which I will maybe skip here. But I would just want to point out that scalings are not, different types of scaling are not created equal, right? So for example, when you have gypsum scaling, they tend to form this highly crystalline structure, and they can exert crystallization pressure, which may actually damage the pores or deform the pore. While you have silica scaling, this is more like a gelation process. They would just form like a gel mat on the top, on top of the surface, which would induce fouling but not necessarily wetting, right? So as you see the SEM image, you will see that with gypsum scaling, they actually penetrate into the pore. Eventually you will have wetting, while in this case, there's no intrusion of the scalene into the pore with silica. So you would not see any wetting, but only fouling. So one very promising and now being actively explored approach for mitigating scaling is to use hydrophobic, super hydrophobic membrane. So these membranes, they do not only have very high water contact angle, but they have very, very low sliding angle. So if you you tilt the angle by only a few degrees, the water droplet would just slide down. So some people also call this slippery membrane, but I just keep it call it super hydrophobic membrane, because slippery membrane actually represents something else in the material science community. So the few mechanisms that possibly contribute to the scaling resistance of super hydrophobic membrane. It's very difficult to actually quantify them, like what percentage this contribute, but I would just talk about each of them. The first is to the reduced surface area, because usually with this super hydrophobic membrane, you would have less contact between the water and the solid, right? So there's less area to adhere to. And also usually you have a lower surface tension, lower surface energy of the solid material in order to make such super hydrophobic membrane. So based on thermodynamics of nucleation, you also have a less likelihood of nucleation with this low surface energy surface. Now the last one, which I personally speculate is maybe the most important, is actually the hydrodynamic effect, right? So with this slippery or this long, we call the slip boundary condition, basically the hydrodynamic is not very favorable for the scaling to occur or for it to adhere to the surface of the membrane and got stuck inside the pore of the membrane. While in the case of conventional hydrophobic membrane, right, you have this partial intrusion where the scalene can actually form and form some really strong anchor inside the membrane that makes the scalene very, very difficult to be removed. So in order to make super hydrophobic membrane, you really only need to do two things. First, you want to have a surface that is really, really rough. And the second is to want to reduce the surface energy of that material. So there are many different methods to make it. So recently we have a method, we published a paper where we basically combine electrospinning and electrospraying and try to use this these particles to create a surface roughness, but use the fiber to kind of lock these particles so that they would not be, they would be robustly maintained inside the structure. And then we also use solvent welding to make sure the structure is very, very robust. So here I'm not going to talk about the details, but the membrane actually experienced a lot of hard conditions in terms of hydrodynamics and the chemical and high pH, no pH, and it's still very stable, maintaining super hydrophobicity. So the membrane, the SEM image looks something like that. And this is the membrane that we're talking about here. So the surface, the contact angle is really high, above 160, and the sliding angle is less than 10 degrees. So it's super hydrophobic. So as you can see here with sodium chloride, the super hydrophobic membrane basically is completely scaling resistant. So even when you have precipitate of sodium chloride in the bulk, you still don't see any flux decline with the super hydrophobic membrane. While with conventional hydrophobic membrane or electrospun hydrophobic membrane, you see significant flux decline. But with gypsum, even super hydrophobic membrane is not enough. And we suspect that this has something to do with basically the crystal formation and intrusion into the pore, which eventually would basically deform the pore. So with gypsum scaling, super hydrophobic membrane can mitigate to a great extent, but still you see flux decline as you recover more and more water, and eventually also have a little bit of wetting as well. So really the last piece of work that I want to talk about is the combination of operational strategy and material strategy. So here, what we can try is to push the scalene back to the feed solution by either doing a gas purging, like air purging, or doing a post flow, right? There's two separate study. So the post flow, basically you periodically reduce the pressure of the feed stream so that you have a driving force to kind of push the scalene back to the feed solution. But it would not work at all if you have a hydrophobic membrane. As you can see, the scalene would actually form these anchors inside the pore. So this just doesn't work at all. Now, but if you have super hydrophobic membrane, which I showed that is still not completely resistant to gypsum scaling, but if now you do this operational innovation together with the super hydrophobic membrane, we show that is actually effective in almost eliminating even gypsum scaling. So these are the experimental data, right? Here we're comparing both the unpurged membrane with super hydrophobic and hydrophobic, and the purged membrane super hydrophobic and hydrophobic. So as you can see, only when you have super hydrophobic membrane and when you're purging the membrane periodically, like I think like once every hour, like 1 minute for every hour, then you can maintain their almost perfect water flux, even when you recover it to a great extent. So this highlights the importance of both the synergy between material innovation and also operational innovation. So to summarize, hydrophobic membrane is actually bad for a lot of reasons. So it's easy to be, is susceptible to wetting, to scaling, and to fouling. So people have been developing omniphobic membrane. That basically omniphobic membrane is a membrane that is in air oleophobic, but it's not underwater oleophobic. So it's good for wetting resistant, but not for the other two scaling and fouling resistance. So superhydrophobic membrane is good for scaling resistance, but not for wetting or fouling resistance. Genus membrane with a hydrophobic substrate is good for fouling resistance, but not for wetting and scaling resistance. So you can try to do some combination like function-driven design, membrane design, for example. When you talk about a case where you have a genus membrane with an omniphobic substrate, right? In this case, the membrane is both in air oleophobic and underwater oleophobic. So in this case, you can achieve wetting resistance and fouling resistance, but most likely this membrane would not be scaling resistance. So there's no one size fits all. So it really depends on what your fit solution is in terms of is like what components it contains, and you have to basically choose the right membrane to basically use for that specific solution. So this is my last slide. So basically, in order to achieve the practical application for membrane distillation, we have several major problems to overcome. But then we also have some too, right? Pretreatment, which is something I did not talk about, I think is incredibly important and maybe the most practical approach to address some of these challenges. But then my talk is mostly focused on material, but operational innovation is a very important piece in our toolbox that can help with, especially for example, for scaling control. We really has to combine the material and operational approach in order to get a scaling resistant process. Lastly, a lot of the stuff that I just mentioned actually is summarized on a recent paper that we published on ACS CSD Engineering, a new journal. So if you're interested, you can look up this paper. So these are the authors. These three are my students, and also Professor Tiejun Tong from Colorado State and his student Yiming. So I'd like to acknowledge my group. So these students, they work on MD. They're from my group, and this is the visiting student Chen Lei, who contributed a lot to the superhydrophobic membrane work, and Professor Tiejun Tong, who's our collaborator from Colorado State. With that, I would like to thank you very much for your attention.
Thank you very much, Professor Xion Lin. Great presentation. Amazing to see all the details in this MD process. Is there any questions from the participants? Maybe as people are thinking about questions, I was just wondering, what is the, I suppose the more effort you put on in designing a membrane with different materials, it probably becomes more expensive, the membrane, I'm guessing. So what is the trade-off maybe between a super designed membrane over or varying other components of the process? What would you think would be a good balance maybe?
Yeah, that's a good question. I never think about cost really, because we, like in our lab, we mostly focus on the fundamental aspect of it. But for example, omniphobic membrane, as I said at the beginning, people like do nanoparticles and all that. But now people realize that you can just simply modify a commercial membrane by making further reducing the surface energy. So I think like there's certain way. So there's definitely ways to make all this modification more practical, right? So the less step you use, the less component you use, the more practical. And lastly, although my talk focused on material because this is the theme of this session, but I really think that pretreatment has a great, like very, very important role, and maybe the most practical approach in mitigating a lot of these problems. So I would say you want to do very extensive pretreatment first, and then this membrane is just to basically serve as the final safeguard to addressing these problems.
Great, thank you. There's another question from the audience, from Professor Supantra Singh. He asks, what is the role for texture to make hydrophobic or amniotic membranes?
Oh, that's a great question. So as I said, for super hydrophobic membrane, you really just need to have very high, large roughness. So just like make it really rough. For example, put large particle on the surface and then put small particle on top of the large particles and all that, right? So it doesn't matter what type of architecture those roughness are, right? Just a lot of surface area. For reentrant structure, you really like the key for omniphobic membrane is really the reentrant structure. Roughness is not that important. It's really the reentrant structure, which basically you need to have structure with small opening at the top and then larger opening as you get deeper. And the idea is really want to have the expansion of the water-air interface as it moves downwards. As it moves into the membrane, it expands, which is thermodynamically unfavorable. And that would give you this metastable non-wetting state. So that's the key for omniphobic membrane. Reentrant structure basically is the key.
Great, thank you. Okay, so in view of time, I think we'd like to move on to the next speaker. Thank you very much again, Shihon, for that great talk. So now I'd like to introduce Professor Louis de Smet from Wageningen University and Wetsis in the Netherlands. And he'll speak to us today on the recent advances in ion selectivity with capacitive deionization. So Professor Louis de Smet, please, the floor is yours.
Thank you very much, Chris, for both inviting me and also introducing me to the audience. If I'm correct, it's the full screen that you see now? Yes, okay, thank you. So what you see on this slide, apart from my name and the title, is two pieces of art that contain a pigment, a blue pigment, PBA based. So that is the structure here on the right. It's Prussian blue. It's iron hexacyanoferrate, and I will talk more about that because you can not only use it to make nice art, but also to remove ions from water, the topic of today. And what you also see on this slide is a map of my country. We all know that we're supposed to be in Israel now, including Drylands and the deserts, but the Netherlands is a very different country. Luckily, we have the dikes here that protect us from the seawater from the North Sea, but if they would not be there, quite a portion of our country would be wet. So one part of my affiliation, Wageningen, that's still okay without the dikes, but Wetsis, which is here, is in Leeuwarden, would not be okay. So we're very happy to have the dikes. Also happy to be here and to continue now with the science. We already heard a little bit, quite a bit on membrane distillation, which is one of the biggest techniques used to desalinate water. So you can do that with or without membrane, of course, distillation, sorry. And there you use heat or a difference between two temperatures to transport the water and to get it desalinated. The second best in terms of abundancy is reverse osmosis, where also membranes are used. Again, you remove water from the salt, and now you don't use heat or a difference in temperatures, but you use a different pressure. And another one, but it's only 6%, is ED, electrodialysis, where both membranes and electrodes are used. A disadvantage could be that there is some side reactions that produce hydrogen gas and also oxygen. And here the focus is of this technique on non-porous electrodes, just to have an electrical field to make sure that you can move your ions to a certain electrode. And I will be talking about porous electrodes, so not distillation, RO or ED, which are quite a bit used to desalinate water, but I will tell you about the use of porous electrodes and tell you also where they fit into this scheme. So I will show you where the sweet spot of CDI is. It started already in the 60s of the last century with a study here, electrochemical demineralization of water using porous electrodes at a large scale or large surface area. with this study. And what you basically do is you have two parallel electrodes, an anode and a cathode, and depending on the charge of the electrode, it's either the cations or the anions that are electroabsorbed onto and into this material. And so what you have is you temporarily store the electrons into the electrode until you switch the direction of the field, and that enables one to get them released. So you could then desalinate water in one stream and then recollect the ions in a second stream. This technique cannot be compared with the three ones on the previous slide in terms of desalinating seawater or at least water with high concentrations. It does work, however, for brackish water. And also, if I move on, a bit slow, but there it goes. You can use it because you address the ions, not the water, to see whether you can use this platform to remove ions in a very selective way. And if you then look into literature and also the way our group is approaching this interesting field of combining a desalination approach by fishing for the proper ions, is you can work on different aspects of the electrode, as well as you can work on membranes or materials that are covered onto such an electrode. So part A of my talk is about the electrode, and the second part B, is on doing chemistry onto the electrode. Before I do that, a short overview of literature in terms of ion selective CDI. Currently, a review or manuscript of us is under revision, where we give a huge overview, I would say, on using CDI not to desalinate, but to fish certain ions, ideally in a selective way. And I want to show a few overview schemes from that manuscript that will guide you to see what is the state of the art, and then later on how this work fits into that scheme. Before I do so, no need to read the whole table, of course, but a few aspects related to how to define ion selectivity. There are several ways, and that makes it also, as always, when you try to have an overview of a certain field, it also makes it a bit complex. But the top two, which are S and rho, they focus a lot on the influent versus the affluent ion concentration. So here we look at binary systems, but of course you could expand this to bigger series of ions. And rho, that's in the second entry, is basically the same as S, at least if you give it the system until infinity. So, and the first one is an integral. The second one is if you compare the start with the final situation. But often also R is used, and then interestingly, because there the focus is on dividing the affluent concentration by the feed concentration, it would give the opposite value. So where S and rho go into a certain direction, say above 1 for a certain system, the same system for R would give a value below 1. So that is something to take care of when you compare the selectivity values in different studies. Also from that manuscript, an overview of generalized selectivity mechanisms for porous carbon. Porous carbon is the material that is often used to make these porous electrodes. 8 panels, so A and B focus on the surface and the electrostatic affinity. So basically, if you have a negative electrode, you would affect cations. Ion sieving is then a bit of kind of size-based exclusion. So smaller ones that can fit will fit, and bigger ones that do not fit into the porous materials, porous electrodes, they are not electroabsorbed, maybe at the interface, but not at the overall interface into the bulk. The next panels focus on differences in solution. So ions may have a different ion diffusion value. So that would then be a kinetic way of separating ions. And also an important parameter is the hydration energy. Two other aspects is affinity towards certain functional groups. So you could modify your electrode via chemical means, and then you could try to address for certain ions. And what you can also do is you can cover it with something. You can coat it with certain different chemistries. Could be a membrane, could be a modified membrane, and there also the aim is then to tune selectivity. And the last two, the first one is a bit related to the hydration energy, but now within one series of ions or monovalent in this case. So you look at or you probe for the difference in the hydration ratio. And the last one would be not really charge-based, but more electro affinity or electronegativity based. So no full charges here in terms of the electrode, but again playing with the chemistry. Okay, I move on. So as I mentioned, it's typically carbon that is used in CDI, CDI, capacitive deionization. So we call that the classical way of working, where ions are stored into the electrical double layer that is present in this porous material. That's done a lot already from the beginning, and over the last years, there's also a non-carbon branch in the field of CDI. That here is indicated with some batteries, because what we see is that there's a lot of different types of materials being used in energy storage, and some of them also made it to the world of desalination. One example here is the blue pigment on the very first slide, where we have a lattice made of iron and nickel and also nitrogen and carbon. So the nitrogen and carbon are into the hexacyanoferrate moieties. And what can happen is when you play with a redox state via the electrode, obviously, of this lattice material, that an ion can be inserted upon the oxidation. Upon the reduction of one of the irons that is here part of the corner. So you play with the redox state of your material to insert or expel ions in and out from your material. That started with a lot of non-carbon based, although this is of course a cyanoderivative, and also some more carbon-based methods are used in here. But they are very different compared to the classical carbon, because here it's the EDL where the storage is taking place, and here is really insertion into the material, which is then often called intercalation. And of course, depending on the sizes in the pores of porous carbon, but also the lattice parameters of your intercalating material, you could try to make a system that is then allowing the uptake of the smaller ones with respect to the bigger ones. So that is then one level of selectivity already. Not too long ago, last year, we reviewed the field of how the intercalation materials are being used in CDI. And then again, it seems, start digging that completely out, that it already started a while ago. First of all, by addressing the the Prussian blue redox activity. And then already in the mid-80s, it was used to look at how you could insert a metal into that. And then in the late 90s, it was shown that you could use of switching the ion exchange in an electrical way. And then more recently, it was not only PB, but also NMO and NTP, so abbreviations for, let's say, more, to me as an organic chemist, more exotic materials that are used a lot, again, in the field of energy storage, but now also in CDI. And if you then continue to even more recent work, then let's say since about 3-4 years, you see that there's also even more materials being used, all taken from the field of energy storage, and also the theoretical understanding of this whole intercalation process in relation to CDI is better understood. Back to this PB and PBA. So PB, Prussian blue, is then the structure which was also on the first slide. So we have iron 3 hexacyanoferrate 2, this lattice structure. And if you now replace one of the irons, so not in this part of the molecule, but in this part of the lattice by a nickel, then actually the Prussian blue is not blue anymore. It's green. So we call this a Prussian blue analog. And this analog is used in desalination electrodes. How do you make these electrodes? Well, you can start from, there are different recipes, but the one I present here is nickel dichloride with this sodium iron hexacyanoferrate derivative in water. You mix that and then you get a precipitate that together with this in a salty solution basically, that you can harvest from your solution. And if you then combine it with 10% of carbon and also 10% of binder, you can make sheets out of that, cold rolled. And if you then continue studying them, you will learn from electron microscopy that you have them at certain particle sizes. That's not clear from here, it's 2 to 7, but here you see the micrometer size clusters of that material. And then you can coat them or you can roll them in a certain thickness. So here the one is a few hundred thickness. And from XRD, you can learn about the lattice parameters. And in this particular case, for this chemistry, it's about 1 nanometer, a certain characteristic of this material. So that was already done at WETSUS in collaboration with Carl Smith 3 years ago. And we continued on that in terms of ion selectivity. Before going into the ion selectivity, I need some time to explain differences in the working modes, the mode of operation when you try to compare, let's say, the classical carbon-based way of desalinating water with CDI versus the more this other line of research on intercalation. So on the left, we see again the two parallel structures, electrodes that are covered with ion exchange or cation exchange membrane to prevent co-adsorption and also to increase the energy efficiency of CDI. And what you do is, again, so you have salty water, you make it less salty, you can make it fresh, and you can harvest the electrodes when you have a second stream. The interesting thing about using intercalation materials is, especially when you combine it with one single anion exchange membrane here in the middle, which was reported for the first time by, again, Carl Smith. The interesting thing is that you do the two things that require 2 steps in carbon-based CDI, but here you do it in one go. So you have one chamber, so to say, one stream of water that you desalinate because there's uptake, or intercalation of cations into the electrodes. But at the other electrode, there is the release of ions that were already bound onto the electrode into the water. And that makes it very energy efficient, as we will see in a minute from now. So here we have, of course, also anode and cathode, but it should be realized that they are of the same material. And we only address cations in this particular case, whereas in carbon-based CDI, we address both the anions and cations in terms of electroabsorption and desorption. So building further on that, so this is a crucial difference between the two schemes. And this is then also reflected, of course, in the data. For example, the one on this slide where you see differences in the concentration over time. And over time, of course, is not only time, but also switching events between the direction of the electrical field. And well, you can discuss a lot about the shape of these plots, but what is especially clear when you compare left with right hand picture is that on the left, you see that in one go, there's one stream in which the concentration goes down, whereas parallel to that, in the other one, it goes up. And that is very different from the carbon-based scheme, where the concentration goes down and can go up again and down again if you, of course, continuously recycle your stream. Well, that's obviously not what you want. If you want to desalinate, you have to switch between 2 streams, where in this scheme that's already taking place in one go. So the loading and unloading is different. So we have electroabsorption and desorption for carbon-based, and we call it intercalation and interdecolation, or let's say uptake and release via the redox states into the electrodes in the intercalation type of working on the left. But the differences in the delta concentration, the difference in concentration that you can obtain is in the same range. I continue also by comparing another interesting parameter before I go to the ion selectivity part. And that is what about the energy and also the average salt absorption rate. First of all, I have to mention that, so we use the two cells I have just discussed. I hope that is clear, that difference. And we kept as much as possible identical between the two sets of experiments, but using the two different types of electrodes. So fixed inlet concentration, fixed flow rate, as well as the electrode area, which was constant, and also the flow channel thickness. And then what you see here in gray, it's the PBA, so that's the intercalating type of desalination. And then red is MCDI, so that's membrane-based CDI. So two carbon electrodes that are covered with either an anion or a cation membrane. And we see that because of this parallel desalination and concentrating in the case of the PBA-based type of material, we see lower energies for the PBA compared to, let's say, the classical carbon-based CDI. So that's a gain here. And also, if you look at the average salt absorption rate, which will be added to the plot now, you also see differences between the two, and again in favor of the PBI. So one benefit on top of that, you can do things in parallel of PBA with respect to CDI is related to the rate of desalination and also the energy. Now we go to the selectivity studies. I was talking about these two streams. So on the left, you would if you go from bottom to top, it becomes lighter. So you desalinate, and on the right-hand side, you would concentrate your water. And what we do now is we switch between, well, let's say what is presented on this slide and the other one. We put the electrodes in the different solutions to make sure that we kind of, it's a batch process, but we make it continuous this way to build up the concentration in the, let's say, in what is called here green, and also the reduction in the red beaker in this particular case. And if you then look at the data and you compare the divalent with monovalent data, you would see that in a scheme like this for PBA, where the lattice parameters are such that monovalent ions would fit and the bivalent ones, they do not, they're too big, you indeed see that also reflected in the data. So this is what you expect based on size, and this is the data. And the data shows us that we have a more or less constant, there's some differences, but more or less constant concentration in magnesium and calcium, so the divalent ions, so virtually no absorption, or intercalation it's called here. But if you then go to a monovalent ion like sodium, you would see upon every cycle, so that is redipping the electrodes in the other beaker, an increase in one of the beakers and a decrease in the other one where you desalinate. So from plots like this, what you can do is you can calculate the selectivity coefficient. So here, for example, rho, where rho for sodium compared to either calcium or magnesium gives us values in the order of 15 to 25 for this particular kind of experiments. So we do not coat the electrode here, it's just the intercalating material, which is PBA here. So that's a nice number, I would say. Now I want to move to coating electrodes. I already mentioned that you can coat a porous electrode with an anion and cation exchange membrane, but I want to now go to other coatings which are polymer based. Of course, also ion exchange membranes are polymer based, but I want to go to a particular kind of polymer deposition technique, which is layer by layer, as it is called. So what we do is we make a multi-layer, and I will explain in a minute how that works, of two different types of polymers, here represented in a blue and in red. So there's a polycation and a polyanion that you can use in what is called LBL chemistry to deposit a layer of a certain thickness, and then depending on the parameters and the characteristics of this layer, you can find a way of, again, rejection of the divalent ones and transport of the monovalent ones. So the transport, again, of course, is driven by the electrical field. And due to the electrostatics being present in these layers, divalent is rejected and sodium can go through. That's not the case for all combinations of polymers and conditions, but there are parts in that window that would fit with this, this cartoon here, as I will show you in a minute. So it was Gero Decher already in the late 1990s who started reporting on these. Well, this is the, oh, this is a mistake. It's not the desalination paper. It's actually a single author science paper. I'm sorry for this mistake, copy paste from my side. So this is a science paper, heavily cited, where he presents the concept of when you have a charged surface and you dip it in an alternating way to into solutions that contain polymers of the opposite charge, that you electroabsorb these physically electroabsorb these polymers onto the surface, and if you have washing steps in between, you can get these multi-layers. So here we go from a charged positive surface to a polyanionic covered surface, and then here there's the bilayer. But of course you can repeat this many times, so you can build up your stack to a larger thickness. And these are the two building blocks we have been using onto our electrodes and also on our membranes. There we can discuss a lot about what is now the optimum combination of well, the combination here, that's one choice, but also the optimum thickness. So we learn a lot from pressure-driven separations that were done earlier by others, and I cannot claim here that this is also optimized for the separation I'm going to show you now, but of course you have to start somewhere, and we will hopefully map the matrix and optimum window also in the future. But here we have 11 layers in total. So 5 of the polycation in an alternating way with 5 of the polyanion, and then there's a polycation on top again. But you can already see that you can play a lot. You can play with different building blocks, thickness, terminal layer, but this is the one I want to present now. And you see, this is not ion selectivity data yet, but there are different ways that you can use to see whether your buildup is going fine or not. For example, by checking the water contact angle of the surface. If there's a certain difference in hydrophobicity, hydrophilicity, you will see that alternating with every next dip. And also with XPS, where you map, as already mentioned earlier today, the top few or less than 10 nanometers of your surface in terms of elements being present. So if you look at the percentage of nitrogen over silver, so one is taken from one polyelectrolyte and the silver is present only in the polyanion. So if you look at the ratio between the two, again, you see alternating plots from which you can learn that after every next dip, indeed, you change the overall surface again with the polymer that you used in the dipping. And you can also look at thickness with different techniques. And if you use ellipsometry, you obtain the optical thickness. And in this particular case, with these 11 layers, it's about 16 nanometer. And this we have been putting onto an ion exchange membrane, which is, of course, multiple of hundreds micrometers thick, but the top 16 nanometers was the 11 layer or 11 polyelectrolyte layer thick coating on top of that. And then, of course, the question is where to start in terms of anion or cation exchange membranes. Well, we have been modifying cation exchange membranes. One is called CMX. It's a standard grade. It's cation selective. And we put our multilayer on top of that. So if we then compare the second box with the first one, it allows us to look at the effect of the multilayer in terms of separation. First of all, desalination, but also ion selectivity. And we also included SIMS, which is a monovalent cation selective membrane. And that allows us, well, we have one additional reference in our study to allow us to do a further comparison with what is used a lot in literature. And then you see plots like this. So here I need to take some time, of course, because a lot of data, but what do we have? We have 3 panels here where we have the effluent concentration as function of time. In the early stages, if you would look at the slope of these plots, there's a relatively high increase or decrease if you want, but high slope, negative slope in the very first seconds of the desalination process. It's leveling off at some point, and then you find a minima in all these panels, and then after a while it started to increase again slowly towards what is then called the catalyst. So the fastest absorption is taking place in the beginning. There's a max or a minimum here around 2 minutes in this particular experiment, and then it levels off again. That can be explained by two aspects related to the type of experiment. First of all, the electrode gets saturated, and secondly, because we have a continuous stream, so the effluent goes back as a feed, closed system. Once the electrodes are saturated and you refresh the solution, then of course the effluent concentration is the one that is the one of the feed. So that's closing the circle, so to say. But of course, the interesting window here now is around this minima. This is the dip in terms of getting the lowest concentration, and the dashed line here, TS, is the time that we identified. Here it was 220 seconds, where we had the maximum rho, so the maximum selectivity. And that's also what we calculated. And if you do that, you get a plot like this. If we add our polyelectrolyte multilayer onto these membranes, we see a switch. For example, here CMX, which is then selective for the bivalent magnesium, the divalent one, so the green bar is bigger than yellow. You see a switch, you see a flip towards a larger yellow bar, which is reflecting the sodium. So we go from a magnesium selective membrane to a sodium selective coated membrane, while the coating is only in the nanometer range. So that was an interesting result, which we published earlier this year. And SIMS, which is the membrane that is only not transparent, sorry, is only permeable for electropermeable for monovalent ions, is doing it better. It has a higher selectivity, but of course the interesting, because here the ratio between this green bar and this yellow one is a bit more in the favor of magnesium compared to here. But of course, we were able to show the switch, which is the key finding here. Here you can see on this last data slide that apart from electroadsorb, the system is fully reversible, and we can also desorb the ions. So we can increase the concentration in the effluent again. And the last two panels show that after a few initial cycles where everything has to get stabilized, after a while we get a pretty constant concentration and current difference and conductivity difference. So with conductivity, we also look indirectly, of course, at the concentration for cycles, what we studied up to 40. Of course, this needs to be further extended in the future, but for the proof of concept of applying these materials onto membranes and coatings, that was already a nice start, I would say. Brings me to the last slide, where I want to give an overview of my conclusions. So the cell with carbon electrodes consumes twice as much energy compared to the intercalating one. Also, if we combine these two identical PBA electrodes with the membrane in between, we see that rho goes up for monovalent compared to the divalent cation. So we see their favor. LBL, so layer by layer, polyelectrolyte multilayer. We see that there's a monovalent ion selectivity, and that upon putting that onto the membrane in a carbon-based system, makes sure, or let's say allows a switch of the selectivity. And as you can imagine, you can use very different polymers, polyanions, polycations, and you can also functionalize them, and you can play with the thickness and many more parameters, showing that after this example here, these kind of materials, and that also is then, of course, related to the intercalating materials, have high potential to tune ion selectivity. This work is funded by the ERC via a consolidator grant, and that allowed me to hire 3 students and a postdoc, all listed here, who did all the experiments, and I would like to acknowledge them as well. And I would like to thank you for your time and contributions, hopefully later on in discussions, either now or later on in a chat. Chris, thank you.
And thank you very much. It was a great talk. Wow, a lot of, you know, we could learn a lot about capacitive deionization and the different types of electrodes out there. Wow, all great talk. So I'll open it up for questions. People from the audience, feel free to ask your questions now.
Hello, I got a question. First of all, thank you very much for the talk. Help me to say hello to Yoger and Martin. Haven't seen them.
Yes, they are not on this slide. Maybe I should have done that, but for sure I will do that. They, yeah, I work very close with them together, especially on the integrating materials. Yeah.
Well, me too. I work with them a little bit in the past few years. So I have two questions. First question is why didn't you use constant current to do the last study that you just mentioned? I think it makes the analysis much more convenient.
To be honest, it's something that we are currently doing. So we started with the constant voltage, and that made us, the plots I just showed you. So, for example, on slide 29, I believe it was. So I should go a little bit back, but then you get plots like this. So that's work in progress, Professor.
Okay.
Yeah.
And also, why? So what's the? I probably missed that, but what's the justification of putting the LBL, the polyelectrolyte multi-layer, on top of the ion exchange membrane? Why don't you just apply that to the electrode?
That would, of course, be also a possibility. However, so what we do now is we combine both the valence-based separation, which is due to the LBL, as well as in the case of when you do this on a cation exchange membrane, also you prevent the anions to go through. So, of course, this very much links to the work of, as presented by first speaker in the first session, Professor Jasby. Yeah, both have their own contribution, either in terms of valency or in terms of charge. An LBL on its own, directly, so without an ion exchange membrane, may also be permeable for anions. Of course, this is not going to happen due to electrostatic reasons of the charge of the electrode, but there's also co-adsorption of the counter ions. That's something you would like to prevent as much as possible.
All right, thank you.
Thank you.
I'd like to ask a question. Is someone from the audience, Professor Sutantra Singh. He asks your opinion on the CDI future as compared to other membrane-based technologies.
Yes, I addressed that a little bit, I think, in the introduction, but I can elaborate a little bit more. So it's hard it's impossible, I guess, with CDI to beat the big techniques, so the heavily used techniques in terms of desalinating water with high levels, high concentrations of salt. What it does add to the field is the possibility of addressing the topic of ion selectivity. Of course, if you use membranes in membrane-based, well, that's vapor-based typically, you could say, especially after the talk also of Professor Jasby, if you would have systems like he described in ED, you would also be able to remove ions in a selective way. But here, of course, you store them into an electrode and you can harvest them. So it's the combination of ion selectivity and also the opportunity to harvest, then reuse, recover. That's what I see as the added value.
All right, great. Any last questions? Maybe one more question. All right. If not, I would like just to thank everybody for attending this session and also people watching from outside the Zoom. And I'd like to thank the speakers again. Thank you all for contributing to this session. And finally, I'd also like to thank my student, Chetan Sharma, who supported this session and last session technically. So I hereby close this session, and I wish you a fruitful conference. You can make use of all of the opportunities, the meeting rooms, and in the next few days, the future talks. So thank you again, and enjoy the conference. Bye-bye.
Thank you. Bye-bye.